Good morning, everybody, or good afternoon for some of you. I've just checked it for the time in Southeast Asia. I checked it for Pakistan and Indonesia. It's somewhere in between 1 to 6 p.m. So good afternoon for everybody in this room. My name is Rizka Bebani, originally from Kurdistan region, working and doing my PhD in Germany. Since I see some participants are still joining us, we will give a couple minutes to collect some more before we start with our today program. So in 2 minutes, we will start with our course. So I would kindly ask you to mute yourself. Opening or closing your camera is optional for you. I think the host is usually closing all the cameras and muting everybody, since we are almost about 200 participants. We still have some places over Zoom to join us. The rest will join us through the YouTube link, and the YouTube link will share it soon also in the chat box. So I will start in a minute.
Terima kasih banyak, Mas Raden.
Again, I'm here. Good morning and welcome all of you to our new training course on lifecycle assessment. I'm happy to moderating the next sessions in the first day of this training course. As I mentioned previously, my name is Rizka Bebani. I am from Kurdistan region, but living, working, and doing my PhD in Germany at the moment. So I would repeat and kindly ask everybody to mute yourself, and opening or closing your camera is up to you. Nonetheless, I have to mention the session will be recorded and shared with everybody. So in case you haven't read the document we have shared, the today course is on life cycle assessment. We have in the today morning session 2 presentations. I am moderating. Afternoon we have one more, and the second day of the course would be on 4th of November, which is on Monday. Since you have received the document regarding the program and the details explanation for our speakers, I would like to give the floor to my colleagues and my friends, Dr. Hania Jalilpur, to introduce you with why Young Professional Group. And after her introduction, we will follow up with the first speaker of the presentations. So Hania, if you are here, I will give you the floor and kindly ask to unmute yourself and introduce YPG to our participants.
Let's see.
Hania, are you here?
Yeah, hi. I'm trying to. Okay, yeah.
So the floor is yours.
Thank you, Asgar. Hi, everyone. Good morning, good afternoon. I'm not sure from which part of global you are joining us today. My name is Haniye Jalalipur. I'm originally from Iran, and I'm also, like Razgar, working and based in Germany at the University of Rostock. Also, University of Rostock is one of the sponsor of today course, which is presented and planned by the ISWA Young Professional Group, the online meeting and discussion working group of the Young Professional Group. I'm giving a short introduction, a very short to you about the ISWA Young Professional. You may also, when saw this course, you saw the name, and maybe some of you were curious to go to the website or search about it. ISWA Young Professional Group is a group under the International Solid Waste Association, ISWA, and it's a group for the young professional who are active in the field of waste management and circular economy, and they are under 35 years old. There are several methods that you can be part of the young professional group. Either you can be a member, paid member, or you can join one of our regional chapters in different countries. Then you don't need to pay. And the goal, the aim behind the young professional is to enable the young professional who are studying or start their career or already have less than 5 years of experiment in the circular economy and waste management, to promote them, to help them with training, with networking. So this is a very good platform if you want to learn and train, and also for the networking, knowing about more opportunities and getting connection with the people of like-minded in your country or in your region or across the world. So I'm inviting all of you to go and check our website to see our different working groups, and on the event section of the website, we are always putting our information there. And also we have a LinkedIn page. We are active also on Facebook and Instagram. So that was all. I hope you all enjoyed the course, and yeah, have a nice training day today and as well on Monday. Thank you, Razgar.
Thank you very much, Hania, for the introduction. So since you have heard from Hania, ISWA Young Professional Group is a platform to connect young professionals around the globe, and you are more than welcome to join a Young Professional Group, but also one of the working group. Our working group is online discussion, meeting, and career development. So we are focusing on online meetings and inviting speakers and experts in different sectors of solid waste management, or in the field of environment, I would say, and inviting participants to get in touch with the experts and provide them with insights into in solid waste management. So the today's session is focusing on life cycle assessment. As I mentioned before, you receive the content of the course about the life cycle assessment. It will give you an insight into the life cycle of the products. But also we have practical examples from our speakers, not only for new products, we also have for solid waste, which is more relevant to our group. And the first presentation of today, we start with Dr. Shabir Gheewala. He will introduce you with the fundamentals of life cycle assessment, the methodologies, some basics. And at the end, as I mentioned, he will give you insight into the practical example of life cycle assessment for products, as well as for some waste. At the end of the session, as usual, we have a discussion time for about 15 minutes. So if you have any questions, you can share in our chat group. My colleague will collect all your questions and we will ask our speakers. If any question remain unanswered, we will collect it in a file and share the answers after the presentations in the next days or weeks, depend on the time of our speakers. Since we are all volunteer, we cannot push our speakers to get back into us within an hour or 2 days. So, but usually it works fast and you get the answer of all the questions you have. So since we have the first presentation in 3 minutes, I would like to invite our first speaker, so Dr. Shabir Gheewala. If you could just unmute.
Hello.
Hello, Dr. Gheewala, welcome and happy to have you. So this is the test to see if the system is working. And I will give the floor now to Dr. Gheewala to share his screen, and then we can start in time. So we can see your screen, but if you put on the yes.
Yes, it's a matter of seconds.
Yeah. Okay, could you please just shift to the next page to make sure if the presentation, oh yes, you can, yes. So everything is functioning now. So you have the floor, Dr. Gheewala, and you have exactly 1 hour for your presentations. I will give you a hint when you have about 10 or 15 minutes before the end of your presentation, just to make sure you'll be in time.
Okay, thank you very much. Okay. So good morning, good afternoon, good evening, depending on which time zone you are in. For me, it's afternoon. And today I would like to give you a very short introduction to life cycle assessment. Normally, I've been teaching life cycle assessment since the year 2001, okay, as a graduate course, a 3-credit graduate course. So that means 45 hours. And my introductory lecture is usually 3 hours. So see, this is a kind of introduction of the introduction. So please forgive me if I'm a little bit faster, but considering the time, I will try to manage a little bit, and let's see how far we can go. Okay. I think that it may be easier if all the questions come at the end, although usually when I'm conducting classes, it's I allow people to ask me at any point of time, but with 200 participants, as I notice, I think it may become a bit chaotic if the questions come in between. So I usually like to start every presentation, regardless of whether it is about life cycle assessment or anything else, with this particular slide. This slide shows the planetary boundaries. Now, you know, the Earth has a capacity to deal with all kinds of pollution. The Earth has existed for billions of years, even before the humans came into the Earth, right? And even after the humans came into the Earth has existed and will continue existing, I think, even if we destroy ourselves. But having said that, there is a certain capacity the Earth has to deal with this pollution, okay? But what that capacity, this is theory, but in practice, in terms of numerical values, what are the capacity? So to answer this question, a group of very eminent scientists got together in the year 2009, and they defined 9 planetary boundaries, which you can see over here on this slide, you know, starting with climate change, biodiversity, land use change, freshwater change, biochemical flows, and so on. You can read it, yeah? And they define certain thresholds. That is the capacity that the Earth has to deal with that. And that is this gray dotted line over here, okay? inside here. So if our Earth is within this gray dotted line, then we are in the green zone or the safe zone or the safe operating space, as they call it. But if we are beyond this gray dotted line, then we are not doing so good. And you can see that this paper was produced last year, and in 6 out of 9 categories, we are already exceeding. So for example, climate change, we are in the red zone. Novel entities means plastics and so on, we are in the red zone. Biodiversity, land use, freshwater, biological chemical change, everything we are in the red zone. So we are not doing too well, as you can see. And the other thing that I would like to emphasize on this slide is that these impacts are interrelated. So if we try to just tackle climate change, but don't pay attention to the other categories, what will probably happen is that while trying to reduce greenhouse gas emissions, we may be increasing something else. So for example, if we say, let's promote biofuels to reduce greenhouse gas emissions, but then to do so, we start to plant more biomass, more plants or more trees, more agriculture for the feedstock, then we have problem with land use, we have problem with biodiversity, we have problem with more freshwater being used, we have problem with biogeochemical flows because we use fertilizers and phosphorus and nitrogen flows increase. So you see, everything is interrelated. So if we say, well, only let's just focus on greenhouse gas emission reduction without thinking of anything else, we will be in bigger trouble than we started with. So this is why we need what we call a holistic thinking, a whole thinking. Yeah. Now, when we say environment, what do we mean? You see, I mean, I've taken this figure from this author below, but he had put troposphere outside the environment, but I have put it inside it. That's why it's adapted. So see, lithosphere, hydrosphere, atmosphere, biosphere, flora, fauna, and the anthroposphere, we are also part of the environment and very much dependent on it. Yeah. So that is the environment, and this interaction between the environment and the human society causes what we call impacts. And then in the earlier days, as I used to say, dilution was a solution to pollution, because, you know, we said that, okay, if you put some amount of waste into the river flow is very large, the waste will get distributed and soon it will get degraded and we don't have a problem. But when the population increased and we started to produce chemicals that the earth is not familiar with, so-called xenobiotics, then the earth was not able to handle it. And now we know for sure, we know for many years that dilution is not the solution to pollution. Then we said, okay, let's treat the waste before discharging them. But from the industry point of view or from the production point of view, that is money down the drain, because, you know, industry want productivity. And if you don't have productivity, if you invest $1 million, you want to get back more than $1 million. But when you invest $1 million into waste treatment, you get back nothing. Of course, you need to do it because of the law, but it's not productive for you. And so you try to find ways to subvert. So a smarter way would be, okay, cleaner production. We produce less waste, so that means we have to deal with less waste. Yeah. So of course, prevention is better than cure. But then even that, you know, it's kind of, in the beginning, it was a bit ad hoc. Yeah, you do something, you do something else, but to make it continuous and to make it system-wide was very important. And we will see why this life cycle or systems thinking is so important. So I often like to talk about the electric car. So the electric cars are being promoted in many countries because they run on batteries. Yeah, they run on batteries, so we don't have urban pollution. Yeah, when you have a diesel or gasoline engine, the so-called internal combustion engine, then you burn the fuel to provide motive force for the car, but then you have pollution. You don't need to be an expert. You can see the pollution coming out of the tailpipe. But if you look at the electric car, there is no tailpipe because it's running on a battery. So there is no fuel being burned inside the car itself. However, I think most of us know very well that that is because we have just shifted the pollution from the tailpipe of the car to the power plant where the electricity is being produced. So if the electricity is being produced via fossil fuels and so on, we have not solved the problem. We have just shifted the problem from the car to the power plant. Of course, the advantage might be that power plant is more centralized. So it might be easier to control pollution at at one centralized location than at 1 million cars, right? So that can be possibly an advantage. But of course, then there are losses in production, so power production. So if you have a coal-fired power plant, your efficiency might be about 30% or 35%, which means to get 1 unit of electricity at the power plant, you need to put in 3 units of fossil primary energy. And then, of course, you have losses in transmission, etc. So, and then there are batteries and so many other things. So the point is that if you want to assess an electric car, it is not enough to just look at the car and the driving of the car, but we have to look at the entire life cycle to get the correct picture. Otherwise, we'll get a truncated picture, which is not telling us the whole story. Of course, when you want to compare it with the internal combustion engine car, the diesel or the gasoline car, you have to do the same. You have to look at the production of the gasoline and so on, and until the burning of the gasoline in the car. So then that comparison will be more fair, and we avoid this so-called problem shifting. Another example, just to kind of warm you up, is if you compare an incandescent bulb with a fluorescent bulb. An incandescent bulb is called a light bulb, but it should be called a heat bulb because the principle on which it works, it has a wire, tungsten wire inside, which is made to red hot heat by passing electricity to it, and that generates light. 95% of the electricity to heat up the wire, the tungsten wire inside, goes off as heat, and only 5% is light. So it is actually a heat bulb more than a light bulb. So, but a fluorescent bulb is far more efficient. It's like it uses about 1/5 of the electricity. So a fluorescent bulb uses less electricity than an incandescent bulb. But a fluorescent bulb has mercury inside it. Mercury, as you probably all know, is a toxic material. And even though we may like to say so, but this is not going to be collected at the end of the life of the bulb. The bulb may be disposed not so nicely in many countries, and the mercury will go into the environment. So then which one is better? Yeah, you have the choice between the devil and the deep blue sea. So here, just to give you the life cycle perspective, many years ago, one company in Japan conducted a comparative assessment of these two kinds of bulbs. And they found that the life cycle mercury emissions from the incandescent bulb were higher than the fluorescent bulb. Now you might think, what happened here? The fluorescent bulb has mercury inside it. Incandescent bulb does not have mercury inside it. So why does the incandescent bulb have more mercury emissions in its life cycle? And that was because a lot of the electricity in Japan back then was produced from coal. Coal has trace amounts of mercury, and that mercury is released when you burn the coal to produce electricity. Now, when you because you use 5 times as much electricity for the same amount of light to light the incandescent bulb as you use for the fluorescent bulb, so the life cycle emissions of mercury from the incandescent bulb were higher than the fluorescent bulb, even though fluorescent bulb physically contains mercury, but the incandescent bulb does not. So once again, you see, we have some kind of problem shifting going on, and life cycle assessment is very, very good at catching these burden shifting. Okay, just one more example. So if I have a car made from steel and a car made from composite materials, if I have to compare them, which one do you think is better? So normally I like to put this to my students and we have a big discussion in the class, but today I will just have to give you the answer right away because we have shortage of time. Now you see, steel is a very sturdy material, okay? But it gives weight to the car. And a lot of the fuel consumption of the car depends on the weight of the car, among many other factors as well, okay? But weight is a very important consideration. But I cannot make a car out of plastic, right? If I just make it out of PET, for example, the thing that you use for the water bottle, then it will be very light, but not safe. So then people developed composite materials, which are light but strong. You will see like in your traveling suitcases, you have fiberglass, etc., which is tough but light. Yeah. So these composite materials are very good. So it can reduce the weight of the car. So it makes the car more efficient and more fuel efficient and uses less fuel in the life cycle. So you think, oh, I've done a great job. I need a raise, you know. But when you come to the end of life of the car, the steel is very easy to recycle, but the composite material is much more difficult to recycle. So you see, now again, you have a trade-off. So as a designer, I will not say that I will just try to focus on reducing the weight of the car, but I will look at the entire life cycle of the car right since the beginning, since the design stage itself, to make sure that I catch that I will have this problem at the end of my life of the car. Not wait till the car goes into production, goes into use, and then when 15 years later it comes for disposal, then I start to think, oh my God, now I have this composite material, what shall I do with it? right? So lifecycle assessment helps you to look at these things a priori, right since the design stage itself. Because at the design stage, you can make changes. At the conceptual design stage, you can make changes. But once you come into prototype and production process, making changes becomes very, very difficult because you have invested already a lot into getting the things together. Yeah. So that's why this lifecycle assessment is very useful as a tool. So we talk about lifecycle management. When you do the design, we look at the whole lifecycle right since the beginning. So we start with new ideas. So first we look at environmentally friendly choice of materials. We try to use materials that are not toxic. We try to use materials that are renewable. We try to use materials that are less energy intensive. Yeah. And we try to consume as less materials as possible. That's lower consumption of materials. Yeah. Dematerialization. We try to do cleaner production. So that means we in the factory itself, we try to have less waste coming out so that we have to treat less, and then try to make the distribution process, which is also part of the life cycle. We try to make it more efficient and environmentally friendly use. So for example, for electricity using materials, products, for example, cars or refrigerators or air conditioners, we try to design them so that they use less electricity during the use phase, because usually for energy using products, the use phase is very, very critical. A large amount of the impacts come from the use phase because cars have a life of 15 years or 20 years, right? And during that, they use a lot of fuel. So the emissions are very large. We try to extend the life of the product. Of course, we don't want to make it immortal because, then we are not doing good. So if I have a car that lasts for 50 years, that is not very good also. Because why? Of course, you can say, I need to produce the car only once, but use it for 50 years. However, what will happen as a result is that I will have newer technologies coming, but I'm still using the old technologies from 15 years or 50 years ago, which is not so good. So of course, we want to extend product life, but up to a certain extent. And then recycling, etc., is also very important. But there are many shades in recycling. I don't have time today so much to talk about recycling, but if somebody asks me a question at the end, I will talk more about recycling and the plus and minus of recycling materials and so on. But so we look at the entire life cycle in this management as well. Yeah. This is one of my very favorite slides. You see, everybody can see that there is a picture of an elephant over here, but there are 6 people on this slide who are blindfolded. They cannot see. They're only feeling different parts of the elephant, and they are making different interpretations based on which part of the elephant they are seeing. Somebody thinks it's a rope. Somebody thinks it's a tree. Somebody thinks it's a spear, but nobody is saying it's an elephant because they can't see it. And this is a very 2,000-year-old story, but it's a very powerful metaphor for life cycle thinking. So if you want to solve the problem, you have to look at the elephant in the room. Yeah. If you look at only one part of the problem, you will come up with suboptimal solution. And suboptimal solutions will not add up to the optimal solution for the entire product. So that is why we need to look at the not only entire product, but the entire life cycle. So that we can come up with optimal solution for the entire system. And that is why systems thinking or life cycle thinking is very important. So yeah, so for example, if you have this simple water bottle, we start life cycle assessment from the extraction of raw materials. So the bottle is made from plastic, different kinds of plastic, but plastic nevertheless. Plastic is made from oil. So we need to extract the crude oil from the ground. That has impacts associated with it. We have emissions to air because when we are drilling the hole in the ground, pumping out the oil, etc., we will have emissions to air. We will burn fuels. We will use resources. And all these will have impacts on human health, ecosystems, and resources, which we call areas of protection. And this human health, impacts on human health, impacts on ecosystems, and impacts on resources is what we are looking at when we are looking at a life cycle assessment or environmental assessment. What kind of environmental impacts are there? So once we extract the raw materials, then that oil has to be transported to the refinery. It may be done by ship, it may be done by pipeline, etc. That also has impacts. Then we will have to refine the oil, produce the monomer, produce the polymer, which is the plastic. All that also uses energy, resources, and has emissions to air, water, and so on, and has these impacts. Then we package it, distribute it. We use the bottle, maybe keep it in the fridge, refrigerator. Yeah. Then we may reuse it, or we may recycle some part of it, or we may incinerate it or landfill it. All these will have impact. So we look at the entire life cycle like this. And so life cycle assessment, or LCA, is an environmental assessment tool. Okay. This is a very long definition, but I try to give you the main point by highlighting that part in red. So it is basically, what is LCA? It's an environmental assessment tool. What does it do? It evaluates the impacts that a product or service has on the entire period of its life. And when we say entire period of its life, what do we mean? Like we saw in the previous slide, we mean extraction of raw materials from which it is made, manufacturing, packaging, marketing, use, reuse, maintenance of the product until the eventual recycling or disposal as waste at the end of its useful life. So that is the entire life cycle. And we look at the entire life cycle because we want to avoid burden shifting from trying to solve one part of the life cycle, but then creating another problem in a different part of the life cycle. Like in the electric car, we try to say that, oh, it's running on battery, so it does not have urban air pollution, but then we are producing more pollution at the power plant. So that kind of thing we try to avoid by looking at the whole life. Now, there are two very standard guidelines for life cycle assessment. One is the ISO 14040 and the other is 14044. And according to these two ISOs, the life cycle framework looks like this. So first we have the goal definition, which is the objectives of the study, the scope definition, which is a system boundary. Then we collect data, which is the inventory analysis. Then we convert that data about what? Data about inputs and outputs, which we convert into impacts. And then we interpret the results. So normally in a logical flow, you would say you define the goal and the scope, you collect data, you do the impact assessment, and you interpret the results. But you see there are double arrows everywhere. And these double arrows means that this process is iterative. So that means we allow, in lifecycle assessment, we allow that sometimes when you define the scope of the study, the system boundary, you decide what is important or what is not important, but you have not yet conducted the study. You are deciding based on experience, right? So when you go to inventory analysis, which is the collection of data, or you go to impact assessment, you may realize that certain decisions that you made during scoping the study were wrong. You're allowed to come back and change it. Sometimes, in a very extreme case, when you come to the interpretation of the study, when you're making the improvement options or etc., you realize that you were asking the wrong question. Oh dear. So then you have to go back and change even the goal of the study, because asking the right question is very important. Please shut your microphone.
Hello, Leo.
Mr. Shepo, please shut your microphone.
I'm good.
Please,
I'm glad to know you're
mute
good.
yourself.
Mr. Shepo, we are happy that you're good, but please shut your microphone.
I'm listening.
I'm listening on Sunday.
Yeah, and then there are many applications of life cycle assessment. So initially, life cycle assessments were developed as a tool for eco-design by production engineers. You may be surprised to know this. Some of you maybe know already, but some of you may not know. And the thing is that life cycle was not developed by environmental scientists or engineers. It was developed by production engineers who were looking for a tool for eco-design. And so that means product development and improvement was one of the first uses of a life cycle assessment. Of course, they were using very preliminary kind of methods back then. But in the last 30 years, etc., then the environmental scientists came in and started to develop better methodologies for assessment. We will see some of them, but not much in details. And now, of course, we have much sophisticated methods than in the past. Yeah. And then it is used for strategic planning by companies, by governments, etc. It is used in policy making. It is used as a marketing tool by many companies and so on. So there are many applications of life cycle assessment, which in itself is quite an interesting thing. I will show you some applications a little bit. I'll touch on them, but not so many. Okay. Now, what are the steps? As we've seen, the first step is the goal and scope definition. So if we define the objective of the study and the system boundary and something called a functional unit. This functional unit is something very interesting. It is defining the quantification of the function of the, it's a very interesting topic and I spend many hours discussing it, but I'll give you one example in a little while from now about what is a functional unit and why it is so important. Okay. So once we define the system boundary and so on, what is important, what is not important, then we go to the next step, which is the inventory analysis, where we collect data about inputs, which is basically the resource use and energy, and outputs, which are the pollutants and wastes, as well as the products and co-products that are associated. Yeah. So we collect this data. Then we have methods to convert inventory items into impacts, which is called the impact assessment phase. And finally, we have the interpretation phase, in which we look at the details of the impact assessment and so on, see what is important, what is less important, how we can improve the thing. Finally, of course, we want to improve, right? So we see how to improve. So all these kind of things we do, which constitutes the entire life cycle assessment. So when we define the goal, we have certain very standard questions that we answer. One is, so the goal of an LCA study shall unambiguously state, this is from ISO, directly from ISO 14040, okay? Unambiguously means very, very clearly. The more clear your definition of the objectives or the goal is, the better will be your study. So we define the intended application of the study, the reasons for carrying out the study, and the intended audience to whom the results are supposed to be communicated to. This, you may wonder why that should be defined, but to what details and which kind of life cycle assessment will you do depends on who is the intended audience. So for example, if you're doing the life cycle assessment to get an eco label, you will do one kind of study. If you are doing the life cycle assessment to compare between two products, you'll do a different kind of study. If you want to do a conceptual life cycle assessment at the very conceptual stage of product development, you'll do a different kind of life cycle assessment. So that is why right since the beginning, we make clear who is our intended audience, because how much data we collect, which kind of data we collect, how we do the assessment will depend on that, okay? And one thing we need to also define is whether the results are intended to be used as comparative assertions. Yeah, so if you're making a comparative assertion between products, between competing products, and especially if we need to display those results to the public, then ISO recommends or insists that we must make a third-party review. That is very important. Otherwise, we should not be making comparisons. Otherwise, you know, I am a company, I compare my product with other people's product and say mine is good. Great, of course, yeah. But so that means you have to pass through a strict critical review process if you intend to make comparative assertions. Otherwise, you should not be doing it according to ISO. Okay, so this is very briefly the definition of goal. Now, let me come to the functional unit. Now, when we want to compare different products, we need to have a basis of comparison, and that is called the functional unit, which is the quantification of the function of the product. Now, if I need something to drink some coffee, for example, yeah, so I can drink coffee in a polystyrene mug. It's a kind of single use, yeah. I can drink coffee in a ceramic mug. I can drink coffee in this very nice, beautiful china, which is the porcelain pottery, right? So now, of course, you can understand that it would not be fair to compare one polystyrene mug with one ceramic mug and one of this porcelain, right? The reason being, because polystyrene mug I will use once and throw it away, but ceramic mug I can use again and again. So comparing one and one is not fair. So then what is fair? To make a fair comparison, we compare an equal amount of function. So we would say something like this. Serve, so this is definition of a functional unit. Serve as drink container for 200 milliliters of hot beverages 3 times a day for 1 year. I have defined a certain amount of function. And now I will compare these 3 products based on the same amount of function, which is the functional unit. So for the polystyrene mug, I need 1095 of them. Why? Because I'll drink coffee or tea or whatever 3 times a day. Yeah. So I need 3 times 365. Yeah. That is 1095. Because I'll use it and throw it away. Maybe some of you use one mug twice, but according to the standard, we use it only once. Okay. For the ceramic mug, you know that ceramic mug you can use a lot. So let's say the ceramic mug has a lifetime of 4 years. So then we will say, I need only 1/4 of the mug. I mean, physically you need the whole mug, but I'm allocating the burdens from only 1/4 of it because the life of the mug is 4 years, but my functional unit is only 1 year. So that's why it's 1/4. And then every time I use the mug, I will put it in the dishwasher. So I will need to have the dishwasher running and I will put detergent, etc. So I will wash it 1095 times. So I have 1/4 of the mug, the environmental burdens from 1/4 of the mug and from 1095 washes in the dishwasher along with detergent. That I can compare now with this 1000 units of polystyrene mug for a fair comparison because both of these provide the same amount of function. Similarly, for the porcelain mug, I'm saying 1/2 unit per year. Why? Because I'm assuming that the porcelain is a bit more easy to break than the ceramic mug. Yeah. So maybe it has a life of about 2 years. So it's only half of that. And then I need hot water and detergent to wash it every time. So 1095 washes. So now, as I said before, comparing one and one of each would not be fair. But comparing 1095 polystyrene mugs with 1/4 ceramic mugs and 1095 washes and half porcelain mug and 1095 washes would be a fair comparison, because we are comparing based on the same amount of function, which is serving as a drink container for 200 milliliters of hot beverages 3 times a day for 1 year. Okay, so this is a very interesting thing. And I could go on for hours talking about how functional units should be defined, because it's very, very critical to make a fair comparison. Okay, so this is something also that we define. Now, when we make a kind of system diagram like this, so this is the diagram of an air conditioner. Okay, so when I have, it's called a split type air conditioner, is the one that we have in our office or something like this. So it's called split type because one part is inside your office and one part is outside. Okay, so it takes the heat from your office and throws it out. So that's why you have 2 parts. So this air conditioner has many parts. So the most important, the heart of the air conditioner is the compressor. And this compressor is made of steel, has copper inside, has plastic, compressor oil, and refrigerant. Okay. And then you have condenser coil, evaporator coil. The condenser coil is made of aluminium, and evaporator also made of aluminium, and steel copper, and so on. Okay, and then cap it. So all these boxes over here are different parts of the life cycle. Okay, and we need to collect data about every part of it. I will just show you one example. So for example, compressor. Now, once I've drawn this diagram, I have to look at the details of each box. I will show you the box of compressor just as an example. So here you see number 3. So you have one compressor. The compressor has crankshaft, a cylinder and head made of cast iron, discharge valve made of steel, rod made of steel, rolling piston made of cast iron, and so on and so forth. Okay. So all these data, once I go for the data collection to the factory, I will collect data about the materials, about the weight of each of the materials, about the production process that is used to transform the material into each part of the compressor. So that is how data is collected. And of course, then that all this data will later on be converted to the potential impacts. Okay, so this is as far as the data collection is concerned. Now, when we come to impact assessment, now, after we have collected the data, we are on the left side of the diagram, the green one. Okay, so we have raw materials, emissions to air, etc. This is the data that you have collected. But what you actually want to know is on the right side, which is so-called endpoints or the damage to human health, damage to resources, damage to ecosystem quality. But that the path between the inventory item and the final damage is a very long one and has many cause-effect chains. So sometimes we stop somewhere in between, something that we call midpoints. Okay, so we have climate change, resource depletion, land use, water use, and so on. So we can do assessment. I will show you some example. We can do assessment both at the midpoint as well as at the endpoint levels. And there are different methods that cater to both these kinds of things. So these are what we call impact assessment. So for example, midpoint indicators for climate change or greenhouse gases, we have the midpoint is the increase of radiative forcing. So we have gases such as carbon dioxide, methane, nitrous oxide, chlorofluorocarbons and all, and we convert everything into carbon dioxide equivalents, which is the carbon dioxide is used as the reference gas, okay? And we convert everything to carbon dioxide equivalents so that we can add it up together. If they are in different units, we can't add, but we need the total value, so we do like that. For ozone depletion, our poster boy, our reference gas is CFC11, one kind of, or R11. This was a very popular fluorocarbon back in the day. Of course, these things have been banned by now by most countries through the Montreal Protocol. But we still use that as the assessment gauge. Okay. Similarly, for all other impacts, you have different kinds of units. Of course, different methodologies also use different units. I just used one method as an example. Yeah. So this is how we are defining midpoints. But if the same impacts we were doing at the endpoint level, then we would see the climate change instead of the CO2 equivalents would be in DALI. DALI stands for, you can look at the bottom of the slide, DALI stands for disability adjusted life years. So how many years of life will be lost or lived disabled because of the impact of climate change? The impact of climate change is not just radiative forcing, which was midpoint, which you saw in the previous slide, but it also effects on human health, such as malaria, schistosomiasis, dengue, etc., which will increase due to the global warming. Yeah. Similarly, acid for ozone depletion, we would have damages on human health such as skin cancer and cataracts, which we can also measure as DALI or disability adjusted life years. But when you come to impacts on the ecosystem, then we measure it as potentially disappeared fraction. There are other units also, but this is one of the commonly used units. How much fraction of biodiversity will disappear as a result of this particular environmental insult? And that is what, so acidification, tertiary eutrophication, ecotoxicity, all these impacts on the ecosystem quality we measure in terms of PDF, not acrobat, but potentially disappeared fraction. And then abiotic resources we can measure in many ways again, but one of the methods is megajoule. So the extra amount of energy that is required for getting the next bit of resource. So normally when we are extracting resource, let's take the example of crude oil. So first, when you want crude oil, we will take the shallowest one, right? The easiest, the low-hanging fruit, the easiest one to extract. Once we finish all that, then we will dig deeper and deeper and deeper to get more oil, right? So that means the more resources I use, the more energy I will need for the next bit of resource, because I've already used the easy one first, the easily extractable one. So that is used as a proxy method for calculating the resource use. Nowadays, there are also methods that use dollars, economic values, for doing the resource assessment. Okay, so these are the different methods. For midpoints, you have many methods. One is like CML. This is from Leiden University, and you can look at it. If you, I'm giving the websites over here, you can learn more about it. So this is one midpoint method. Recipe is a very common method that has been used. You can find it on this website. Tracy is this method has been developed by the United States EPA, the Environmental Protection Agency. You can find more information on this particular site over there. So these are different, many research groups, they develop different methods based on their own priorities and so on. Yeah. You have the ILCD, PEF. This is the European methods. Okay. And you can find them over here, the product environmental footprint and so on. Yeah. And one is Impact World Plus. That is also another midpoint method. Okay, so you are measuring the impacts at the midpoint level. And if you want to go to the endpoint methods, there's EPS 2000. It's a very old method actually, developed by Chalmers University in Sweden. And then you have Recipe 2600. So you saw Recipe 2600 as a midpoint method, but it also has endpoint. So it has, some methods have both midpoints and endpoints. Some methods have only midpoint, some methods have only endpoint. Recipe has both. Okay. Lime is an endpoint method. This was developed by Japan. Okay, you can find information over here. So this is an endpoint method. This again, the PEF or the product environmental footprint developed by Europe has both midpoints and endpoints. And Impact World Plus also has both midpoints and endpoints. So depending on your needs, etc., you would kind of select which method you want to use, whether you want to use midpoint method, whether you want to use endpoint method, maybe you want to use both sometimes. I prefer sometimes using both. And that means you have to select your methods accordingly. Yeah, please, Sohail, can you shut your microphone, please? Thank you. Now, life cycle assessment was developed, the very early germ of life cycle assessment was developed the first recorded one is in 1969. It was done by Coca-Cola Company. And that time it was not called LCA. It was called Resource and Profile Analysis, or REPA. Okay. And then MRI, the Midwest Research Institute, conducted another study, similar studies in 1940 and 1974. These were largely focused on packaging materials, etc. Okay, because the companies were trying to develop better packaging materials for their product, less environmentally friendly. But that time they didn't have very sophisticated tools for environmental assessment. Later on, these tools started to come in. So in the 1970s, etc., there was some work done, but very, very few, because in 1973, probably many of you know, there was the energy crisis. So every research shifted the focus to energy, and people were not thinking about life cycle assessment and so on. But then again, in the 80s, etc., the methods started to develop. People started to again gain information, started to develop the methods for life cycle assessment. But everybody was doing their own thing, you know. This was not so. Then from the 1990s onwards, the ISO and the CTEC, these two organizations, the Society of Environmental Toxicology and Chemistry and the International Organization for Standardization, these two big organizations, international organizations, started to harmonize methods for life cycle assessment. So that is why we have these ISO standards, ISO 14040 and ISO 14044. Yeah. And in the interpretation, finally, after we've done all the work, yeah, we have done the scope, goal, scope, inventory, and impact assessment, then we see the significant issues. So what are the environmental impact findings? What are the critical methodological choices? What kind of sensitivity analysis we need to do? What kind of uncertainty analysis we need to do? How do the results change with that? How robust our results are? Can we say something useful or not? How we can improve? So all these things are done in the interpretation phase. So this is quite the most important part, I would say, in the sense that before this, we did all the scientific work. After finishing all the scientific work, now we need to come to the step where we will convert that to English language so that our users, maybe policymakers, maybe companies, maybe the public, they need to understand the results. So if you just tell them carbon dioxide is 1 ton of carbon dioxide equivalent is global warming or something, and people think what does it mean? So now we translate all these scientific jargon and scientific work into language that will be used by the actual users, the final users, the policymakers or the public or the companies and so on. Yeah. So that is happening at this stage. There are many software available. I've just listed very few over here, but there are many more. These are some of the very common ones. Sigma Pro is there, Gabi, Umberto, TCAs, EcoIT. There are many, many software. So anyway, I don't want to I don't advertise any software. Okay, it's just to give an example. Okay, so now what are the uses of life cycle assessment? So who are the decision makers when we say life cycle is used in decision making? So companies are users. They want to have product improvement. They want to have product development. They want to market. Policymakers are users. When they make policy, they use life cycle assessment to assess their policy in strategic environmental assessments and so on. Consumers, us, we use life cycle assessment like in the eco label. When you have an eco label, then because you don't have the tools to be able to judge if you have 5 products, 5 different kinds of soap in front of you, you don't know which one is better in terms of environment, and you have no way to assess it. But then if the scientists assess it and give you a very complicated result, you can't understand it. So then they will kind of transfer it into an eco label. So they put a label on some product, and then we say, I care for the environment, so I will use that product which has this label, right? So LCA results can be useful for carbon footprint labels, eco labels, and so on. And I've mentioned before the advantage of using a life cycle approach is because we can understand trade-offs between different life cycle phases and between multiple impact categories. And we try to reduce impacts and meet regulatory standards. So this is very, very important. And how has LCA been used by policymakers? So for example, EU is very strongly has promoted it in the integrated product policy, or the IPP. They clearly state, you can use the red part, improve the environmental performance of product systems through addressing the whole life cycle of a product. Okay, so that is why they have this life cycle thinking and think for a very long time, and they have included it. Or it is used, for example, in green purchasing. Yeah, so Japan, Thailand, many countries have this so-called green purchasing. So this is what it is because if companies do life cycle assessment, they say, oh, we spend money to do life cycle assessment, and what did I gain? So the government is a very big buyer. So what the government does is they will say, I will buy products that have a certain label, for example, or have done life cycle assessment. So then companies who are wanting to sell their products to the government, which is a very big buyer, they would be induced to apply for the labels, eco labels, etc. Usually voluntary. Okay, they're not required by law, but they are forced by the market. So if the market demands, then the producers will apply for those labels. So if the government of Thailand, for example, says that I will buy products with a lesser or reduced effect on human health and environment, so then, and I will consider such labels. So then the producers are induced to do the life cycle assessment and apply for those labels. So that leads me to eco-labeling. Yeah. So now, how has it been used by industry? So industry has been using life cycle assessments for a very long time for communication. In marketing, they make sustainability reports, etc. Yeah, they use it for their own products, development of products, for improvement of products, for comparing products. As I told you, the life cycle assessment is a tool that has been developed by the production engineers actually initially. It is used for their own business, for product optimization, for cleaner production, cleaner technologies, and so on. It is used in strategic planning when they want to make plans for like nowadays companies are making plan for net zero, carbon neutrality, etc. So they use life cycle assessment to do their benchmarking and using the results to look at how to improve to come to the net zero or to come to the carbon neutrality. Okay, so I mentioned about benchmarking, etc. They can do life cycle cost accounting as well, yeah, and designer training and so on. So these are some of the, not all, but many of the very common applications of life cycle assessment. We have said this before many times. Life cycle thinking is very, very important, and I emphasize it a lot. Life cycle thinking prevents the problem shifting from one life cycle stage to another stage. It prevents problem shifting from one impact category to another impact category. And if we do not only life cycle assessment is for environment, but we have also other tools for social assessment and environmental assessment. And if we do all of them together in a life cycle sustainability assessment, then we also prevent shifting the problem from environment to economy, from economy to society, and so on. We prevent problem shifting between countries. So sometimes, that's a nice cat. I love cats. So sometimes you have some countries like Thailand have higher emissions than some countries, for example, like Singapore. And one of the big reasons for that is Thailand is a big producer. Okay, it has much agriculture and industry. But Singapore is more service-based society. So they don't produce stuff. So they don't produce rice. Rice, for example, has a lot of greenhouse gas emissions. But Singapore also eats rice, but they don't produce it. So when we talk about national emissions, all the emissions of rice will go to Thailand. But Thailand is exporting rice to so many countries in the world. They are eating the rice, but not getting the emissions. So life cycle, looking at the whole life cycle tells you all these kind of very interesting things as to not just the producers being responsible for the emissions, but also the consumers being responsible for the emissions for what they're consuming. And life cycle thinking helps to prevent problem to future generation. Because when we're doing general life cycle assessments, we don't care whether the emission is occurring today, tomorrow, 5 years from now. We consider it all. So that is why we don't think that, oh, what occurs in the future is not my problem. Okay. No, it is my problem also in terms of sustainability, right? So we look at that as well. So that's why life cycle thinking is, once again, very important for that. Now, I have a very nice example of life cycle assessment, a very, very, very simplified life cycle assessment example I will show you. But before that, let me just summarize a little bit about what are the strengths and weaknesses of a life cycle assessment. The strength, of course, the biggest strength is that it is a life cycle perspective. So it is preventing the problem shifting. We have said this many times. It's preventing problem shifting between environmental issues. It is based on science. So it's not based on feeling. I think this is a natural product, so it must be good. No, I will actually assess it scientifically and show you the result. Okay, so it is very good for this kind of comparative assessments based on rigorous science. Of course, even now the methodologies are evolving because science evolves. As we learn more, we try to do better than we did in the past, right? So that way, this life cycle assessment is based on science. Some of the simplifications that happen is we tend to add up impacts over space and time. So regardless, I mean, not always, but a lot of times, especially in the conventional life cycle assessments, we did not mind where the impacts are occurring. We add them up. We didn't mind when the impacts are occurring. We add them up. So this is sometimes a bit simplified. Nowadays, of course, there is more advancement and people are looking at dynamic life cycle assessments and so on, and spatial life cycle assessments to look at differences in time and space. But these are more complicated, requiring much more data and much more modeling, etc. Okay, so these are also kind of ongoing steps. And best estimate principle. So we look at average. Normally in life cycle assessment, we are looking at average. So if you one-time incident, someday you might have an accident. That is usually not included in life cycle assessment. Okay, we generally look at the average. And life cycle assessment is not absolute. As we have said before, it is good for comparative assessments. Here you see, it's good for comparative assessments. So if I do life cycle assessment of a product, I cannot tell whether it is sustainable, environmentally sustainable or not. But I can, if I do assessment of two products, I can tell this one is better than that one. So it is relative in that sense. Even when we do product improvement, we compare a product with itself. So I have this version and I'm now having an improved or better version. So I can tell that the better version is actually having lower impacts than the previous version, the base version. So life cycle assessment is generally comparative. It's not absolute. Of course, now there are the research groups, that, including my own, who are looking at absolute sustainability by linking life cycle assessment results to the planetary boundaries that you saw on my first slide. Yeah. So we try to link the product life cycle assessment or the service life cycle assessment to the planetary boundary to see whether we can say something about absolute sustainability. Can the earth afford this much impact from this product or not? That is another very complicated story, but efforts are being made. So these are some of the things.
I apologize for the interruption. You have a little bit less than 15 minutes.
Yes, thank you very much. I have my watch right in front of me as well. Okay, so to kind of summarize a little bit, at the base, we have life cycle thinking. This is the idea of that elephant. Yeah, we look at the entire elephant instead of one part of the elephant. Then we have single issues like carbon footprint, water footprint that deal with single impact. Carbon footprint deals with greenhouse gas emissions. Water footprint, as the name suggests, deals with water. So sometimes these are useful in certain contexts, but life cycle people don't like this very much because we look at everything because we want to avoid trade-offs between impacts. We don't want to improve carbon footprint, but deteriorate water footprint, right? So then we look at the next channel, which is the life cycle assessment or environmental footprint that looks at all environmental interventions. Above that, now beyond environment, if we combine environment and economy, we have eco-efficiency or resource efficiency. These kind of tools are there. And then when we combine all of sustainability pillars, which is environment, economy, and society, then we have this life cycle sustainability assessment. So we have life cycle tools. Even for economic assessment, we have life cycle costing. For social assessment, we have social life cycle assessment and so on, which are having kind of similar system boundary as the environmental life cycle assessment, but assessing economic and social impacts respectively. So this is at the top of the hierarchy, okay? But at the base is this thinking process, which is the life cycle thinking. So these are some of the reference. I will leave them with you. You can check them out. I would just like to give you a little bit feel for what a life cycle assessment look like. Okay, I have it's a very old study, but quite a funny one. So I'm going to do a life cycle assessment of 100% cotton t-shirt. This study was done in Denmark. I'm just using their results. Yeah, so a t-shirt. Now, where do you think the life cycle, the impacts of a t-shirt will come from? So what are the, I need to define my product. So I'm defining the t-shirt is made of pure cotton. It is not having patterns, etc. Because I need to have the similar product, right? So I just remove patterns, etc. and just have a plain t-shirt. And I use a black reactive dye because black is having the worst environmental performance. You can have so many colors, right? Black is one of the worst. So that's why I use the worst one. And for the functional unit, I define that I will use a t-shirt for 50 days. So once a week for 1 year, right? And it is assumed that a t-shirt can be washed 50 times. So after 1 year, it's become too old, maybe it tears off or becomes faded, and I will throw it away. That is my assumption. Yeah. So I assume that the consumer will wear the t-shirt once a week. That means about 52 weeks a year, but okay, 50 weeks a year. And so that we assume that a t-shirt you use 1 day and then you wash it. Okay, in cold countries, sometimes they say, oh, why should I wash the t-shirt every time I wear it for 1 day? But in hot countries, you need to, otherwise you don't have any friends left. Yeah. If you use your t-shirt for 3 days without washing, nobody wants to be your friend. Yeah. So let's assume that it is washed every time you use it. Now, so my reference product is 100% cotton. My dye is reactive dye, which is a very bad one. I wash at 60 degrees centigrade because this study was done in Denmark. Okay. So in Denmark, they use warm water maybe. And in some cold countries, they use warm water for washing. In Thailand, we don't use warm water for washing. We just wash with normal ambient. Tumbler drying is used. So again, in cold countries, this drying is very common. In warmer countries, we can dry in the air, right? We don't, but in Denmark, I know I used to study there many years ago. I used to study in Denmark 30 years, 25, 27, 8 years ago, and at the Technical University of Denmark. And I know that once it starts to rain, it rains very little, but rains for 3 days at a stretch, no sun. So the clothes cannot dry. But in Thailand, I just put it out and my clothes dry right away in half a day, yeah, or even less. So, okay, tumbler drying. Ironing is not necessary, but we assume that some people will anyway iron their t-shirts. Now, this depends on culture and whether if you're a college student, then you don't iron it. But if you're a professional, you will iron it. Lifetime is 50 washes that we have said. And we said, okay, average weight of the t-shirt, because, t-shirt can be many sizes. The average weight is about 250 grams. And these are some of the life cycle stages, right? We have to first the fiber production. That means we have to grow the cotton. We have to harvest it. Then we have to produce the fiber. Then we will knit it, make the cloth. And then we will use it, in which we have to wash the t-shirt after using it. We have to dry it, iron it, and then it will be disposed. And in between, actually, we'll have transportation. So now we will look at some impacts and see which kind of life cycle phases are important. So if we look at primary energy, because a lot of impacts associated with energy, we will look at energy as a proxy for environmental impacts. Okay. And you see here, the use phase has the biggest contribution. 78% of the energy use is coming from the use phase. Material and production is about 22%. The rest is quite less. Okay. And in the use phase, the biggest impacts are coming from the drying, because you have to dry in the tumbler dryer. If you dry the t-shirt, it's a very big impact. And then from the washing and a little bit from the ironing. Okay. So these are generally. Now, and also if you look at toxicity, it's slightly different. Here also the use phase is quite important because of the electricity, the toxicity impacts from electricity. But here the materials production, because cotton, if you use certain kinds of chemicals, etc., then the material production is also very important for toxicity. So here you have two things. Okay. So now when we looked at, after we have seen this very results, now how to improve. So how can producers improve the profile? They can make a good selection of choice of raw materials. They can use organic cotton. So then your toxicity impacts will reduce. And you can reduce the waste. In the production phase, you try to not use reactive dyes, which are very bad for the environment. And you try to use fabric softeners to make your clothes soft, so you don't need to iron them much. In the use phase, you can extend the textile lifetime. Actually, you may say the producer can't really tell. The producer is not the user, right? But they can influence the use phase by making the product have a longer life. So then people will be induced to use it longer. And they will try to make the product in such a way that the color will not go out and there will not be color staining. So then the product can be used longer. So that is how the producers are actually inducing the users to use the product for longer. So that's how they can influence the consumer by saying that there is no need to dry, in the tumbler. You can dry it in the sun. And I am producing a t-shirt that does not require ironing. So you can not iron it. So this kind of improvements can be done. And how can consumers, how can we improve? We can reduce the wash frequency. Now, this I said, okay, in cold countries, maybe you can use the t-shirt twice before washing it. Some of my friends, when I used to study in Denmark, they said, no problem. You can wear it inside out. Once you wear it one side and then you put it inside out and then you wear it. So you see, stuff like that. Okay. In that, you can reduce the primary energy by 40%. If you don't dry using the dryer of the washing machine and you can put it on the clothesline, there you can reduce your primary energy by 50%. If you don't iron, okay, there'll be smaller contribution, but if you have removed your contribution from the drying and washing, then iron becomes more significant, and there you can reduce. And you don't go to the shopping mall in your car just to buy one t-shirt, right? That is very, very environmentally not friendly. Yeah. So if you don't do that, then you can reduce your energy consumption and so on. So what is my green t-shirt? It's a white t-shirt, but it's green in terms of environmentally friendly. I halve the number of washes. I don't dry. I only 10% of the time I will iron it. I will double the lifetime. That means I'll use it for 2 years instead of 1 year. I produce it in organic cotton. And then my primary energy and impacts related to energy are reduced by 75% by doing all these things. My toxic impact can be reduced by 95%. You see? So this life cycle assessment gave me these kind of results, that if I make this so-called green t-shirt, I can reduce my impacts so much. And consumers can induce by choosing. Normally, producers don't want to produce organic products because consumers don't want to buy, because they might be more expensive and so on. But if consumers demand, producers will produce. It's always this chicken and egg situation, Consumers say we don't have products in the market, so how can we buy? Producer says people don't buy, so why should we produce? So which comes first? Hey guys, it's a very nice diagram, but don't spoil my slide, no? You're making modern art on my slide. I am not whatever, you are not. Okay, you are not. But if you were, then you would be. If you think, then you are. Yeah. So you are not, so you don't think. Please think. Anyway, and producers can produce the better shirt by having this non-iron textiles, having lower dryer requirements like nano shirts, etc. In Thailand, they are very popular. Nano materials, which require very less drying time. The water just goes off like from the back of a duck. Yeah. So you don't need so much drying and so on. Yeah. And then you use better kinds of dyes, etc., which are not reactive dyes and so on. So in this way, you can help to the life cycle assessment results help you to improve your product and reduce the impacts on the environment. So with that, I would like to end my talk because I think I've come to my 1 hour. I thought I had 1 hour, 15 minutes before, but now it seems I had 1 hour. So never mind. I think we are good. So we can have more time for questions. Thank you very much for your attention.
Thank you very much for the very practical example we all see on our daily life about t-shirt, about car, all the practical examples, not only theoretical. If you still have some slides you really want to go through, you can.
No, I had these slides only, but I just said I went a bit faster because I wanted to kind of finish within the allocated time.
Good. Well, shukriya again for the very, very intensive overview of all the criterion. As usual, we have a bunch or a lot of interesting questions. I will try to pick as many questions as possible. If any questions remain, as I mentioned at the beginning, we will share the answer after the presentations when we get the answers from our speakers. So there is one question from Mariam Khalid about the difference between end and midpoint, but I think you have covered in the next slides after the questions was shared. So I go to the next question from Kaisa Jamal. The question is, there are different impact assessment methodologies to estimate life cycle assessment results, but now how can we ensure which one is more accurate, or in other words, which one quantify results that are more precise?
It's a very good question, I would say. And we have tools such as uncertainty analysis and sensitivity analysis, which we use to kind of give a band of results. Life is complicated. Yeah. And in reality, when we assess something, we cannot have an exact value. So normally we have something which we are confident within a certain range. So when we do these kind of sensitivity and uncertainty analysis and so on, we give this range within which our results are valid. So that is how we kind of try to deal with the issue of accuracy or precision, I would say. Yeah. So the more data you can collect, and the better your method is, you can reduce this range. So you become tighter and tighter. But this range is going to be there because there is no perfect solution. We keep improving.
Just as a note, we have enough time for the questions. So if you would like, you can go through a little bit detail into the questions. There are a couple questions regarding the software you have mentioned, like Gabi and some others in different continents or countries. There are a couple questions if they are openly accessed or how to access them, and which one do you suggest? I think you mentioned you are not advocating to any.
No, I'm not advocating anyone. So I use SEMA Pro, but that's not an advertisement. Okay, it's just that I happen to start with it back in the year 2000 with SEMA Pro at 2001, and since I've been using it since. But it does not mean that it is the best or something. It's just I'm more conversant with it. But you can do lifecycle assessment even with Microsoft Excel. I often just use kind of a spreadsheet to do many of the simpler assessments. There are also open access tools like OpenLCA is there. So those are freely available. But the issue with is also that you need a lot of data, and when you want to use, for many cases, you cannot collect every data possible in every lifecycle assessment. So we need databases, and databases, especially the very popular ones like CoInvent, etc., they're not free. So even if you have a free software, you still need the databases. You need to buy that. Some databases, there are also free databases are also available, but there are also those that you need to pay for. So it depends. Yeah.
The next question from Siput Huria. I apologize if I pronounce the names not correctly. Different names from different culture and societies. The question: what criteria should be prioritized when selecting an impact assessment methodology to ensure that the life cycle assessment result align with the specific goals of the study?
You have almost put the answer in your question. So to align it with your goal, yeah. So depending on your goal, what it is that you want to assess, there are many things. I mean, sometimes we go for familiarity, but sometimes whether you want to stop your assessment at the midpoint or you want to go until the end point. Sometimes, like for example, if you are doing a study in Japan, then using the Japanese method might be useful, yeah. Or if you're doing the assessment in the US, maybe they want to use Tracy, yeah, their own software and so on. So there are many such criteria are there to select. I could actually talk more about it later on, but for now, I would say that it depends on the goal and what is it that you wish to achieve. You can select your method based on that. Now, for example, if you're doing the study in Europe, then you would have to use PEF, the product environmental footprint, because they insist on that. So these are the things you have to look at. You have to look at your user and what they demand also.
So since you have a bunch of questions on endpoint and midpoint methods, so the difference between midpoint and endpoint methods, our colleague, the next presentation will also cover this in a specific context of organic waste compost. But I would also like to ask you if you give just an overview about the endpoint and midpoint methods. Of, you had it also in your slides, but maybe more detail.
Yeah. Okay. Maybe just give me a minute. I would like to maybe pull out some slide which is not there in my lecture, in the lecture that I made the presentation.
Yeah.
But yeah.
Yeah, take your time. I will pick a couple more questions till you prepare your slides, since we have some more questions. But some question, if I leave it, the next speakers will also cover some of your answers. So just don't worry if I skip some of the comments from your sides. We had many questions on this endpoint and midpoint methods. So it was
so since it is so
important for
the
audience.
audience, so let me show you. So you see, it's like this, something like this. So this just I'm pulling out from. So when we do the inventory, we get all the inventory results here. And what we want is the final damage. Yeah. Cancer, respiratory disease. But sometimes we stop in the midpoints here in the middle. Now, what it means is, like you see, you have the elementary flows, which is your inventory. Your endpoints are here. And these midpoints lead to these different endpoints. And why we make this distinction is because we cannot jump directly from here to here. We cannot go from the inventory directly to the endpoints. It has to pass through many steps. So for example, this is the example of acidification, right? So if I have sulfur dioxide, which is an acidifying gas, 1 ton of sulfur dioxide coming out, the first thing it does is it reduces the capacity of the soil or the lake to reduce acid neutralization. And that will result in the decrease in pH. So this is a midpoint. But then when the pH of the lake, for example, decreases, then more metals that are bound to the sediments will come out into the solution, into the lake. And that will have a toxic impact on fish. And that will kill the fish. That means fish will die. You will lose habitats. You will lose species. And you will have financial loss to society. And that is your endpoint. So the reason for showing you it in this way is that there are each arrow over here is a cause effect. And each cause effect has to be modeled separately. So there is a lot of cause effect from going from the inventory until the endpoint. Sometimes we say we just want to be very simple, but confident of our science. So we stop here at this midpoint or at the pH midpoint or something like this. Usually we stop at this hydrogen ion concentration because we are very, very sure of the science. We know how to do the calculation. But you know, when you go this and then it goes into the lake and then how much effect, every cause effect that you go, more and more uncertainties are introduced. So on the one hand, you introduce more uncertainties, but on the other hand, the results is more easy for you to understand. If I tell you the hydrogen ion concentration increased by or the acidification increased by 10 kilograms of sulfur dioxide equivalent, you may think, oh, yeah, and so what? But if I tell you, because of this release of sulfur dioxide, you lost $10 million. That is much easier to understand, right? So endpoints in that sense, they make more sense. They are easier to understand. But for the midpoints, we are more kind of confident about the science. Yeah, something like this. So there is this trade-off. Depending on what it is that you want, you can make your decision whether you want to go for midpoints or endpoints. And different methods offer you different kind of, at what level the midpoint will be, what will be the endpoint like, what will be the units and so on.
Thank you very much. The fish example is related to me. I was a project supervisor for a project. It was, of course, not a life cycle assessment, but a practical example for a lake in Germany. And we had faced exactly the same issues regarding the fish and the quality of the sediments.
2024.
Vakas, please
try to mute yourself. We're still not through. I'll go to the next questions from Heiler. Professor, as we know, life cycle assessment study starting from raw materials to end products. What challenge had been faced with your exposure, your experience of the challenges?
And one of the biggest challenges in life cycle assessment is getting data. It is the most time-intensive and effort-intensive part, collecting data. The
data collection.
Data collection is the most important. Yeah. The impact assessment and all, then it is easy for us as users. That is difficult for the people who are making the models. They keep making better and better models. So for them, it is difficult. But for us, we just need to use it. But as users, the inventory, collecting the data is probably one of the most difficult part and time-consuming part.
One more questions from Mariam Gul. Kindly guide how to do cradle to get to grade life cycle assessment. Like
it's the same, but we just have a smaller system boundary because many times we don't need to go until the grave. Yeah, especially for certain kind of comparisons, etc. Cradle to gate might be sufficient. So if I'm comparing two kinds of biodiesels, for example, I don't need to go into the combustion part of the biodiesel because they're the same. Or if I'm comparing ethanol produced from cassava with ethanol produced from sugarcane molasses, then I don't need the distribution and combustion end part. So I can just go up to the production of ethanol because that is sufficient for me to make the comparative assessment. So it's just that, okay, with the cradle to gate, I need lesser data. Good.
Thanks. The last two questions I have here, one from Yash Aryan. It is said that uncertainty increase when we use endpoint impact indicators compared to midpoint indicators. What are the reasons for increase in uncertainty?
Because you see, we keep every cause and effect has to be modeled, right? And every cause effect, every time you make a model, there is some uncertainty because science is not so perfect that we can do exact assessment. So as the number of arrows increases, you keep on adding uncertainties. Yeah.
Mm-hmm.
You imagine that on the one hand, I want to say, if I have 1 kilogram of carbon dioxide going into the environment, how much the heat carrying, the heat capturing capacity of the atmosphere will increase. We have very good science for that. But now to translate that into how much the temperature of the earth will increase, how the ocean currents will change, how much the wind patterns will change, how much the sea level will rise, how many people will be displaced, how many people will get malaria and die because of the increase. Very, very complicated, right? But that is the end point, right? How many people will die? How many people will get displaced? How many people will suffer from malaria or schistosomiasis or some disease? Very difficult, no? That is why the uncertainty increases with these endpoints, because there is a lot of modeling and a lot of choices to be made. It's easy to conceptualize, but very difficult to accurately model.
I hope we answered your questions, Yash Aryan. The last question is from Mohammed Kotaish. What dictates when to use an endpoint method versus a midpoint method? It is the scope and goal, or it is data availability, or there are other determinants?
It's usually the goal and the scope. Who you're doing the study for, what you wish to achieve from that. That is usually the thing that will determine which one you want to use.
Mm-hmm. So the questions, we still have it open, as I mentioned previously 2 times. We will share it with our speakers and we will get you all the answers with the slides of the presentations and the recorded session. Just stay tuned, and for now we are ending the
I have a lot of criteria there, but I mean, we'd have to spend, another half an hour to just go through all this how to select an LCIA method. As I told you, I do life cycle assessment. I teach the whole course for 45 hours. And today you're asking me very advanced questions in a 1 hour introduction. So, I mean, I have so many things I can say, you see. There are so many points I can discuss, but it will take time. So sorry about that, but I hope that at least I've induced you to ask these questions. And that is important.
The apologize came from our side, from online discussion meeting group. We try to, if possible, to manage next course, a training course on the advanced life cycle assessment. This was the basic and fundamental for this time. So if you promise us for our next training courses, we booked only about 1.5 hours of your time today, and we know you have a flight.
Yes.
So we appreciate your time for today's presentation and all the practical example. I was so surprised and get into your slides. I was like getting back to sit and listen as a student. So we thank you again all from ISWA Young Professional Group, and on behalf of my colleague from Online Discussion Meeting Group. If you have any more comments, you can still share. If no, we will let you rest and prepare for your flights, Dr.
But do you think is it possible to have a nice group photo? We have so many nice students, so many people joining the course. Do you think it's too ambitious?
Like on online, you mean on the screen?
Online, yeah, just nice. If
Of
somebody,
course, it's possible if everybody could just
yeah,
click the
well, let's have
camera.
it's a nice memory.
Then I will ask my
And please
colleague
share
if
with all
someone
of us
can
also.
take the picture. Shiza, are you here, or Cynthia? Can you take a picture, or Hania, someone from our team?
Yeah, I am here, but we need to, I think, change the setting so I can see everyone.
Okay, so who is the host now? Right now, the
You are
Ashkri.
the host.
Okay, Hania, I will give you the host. Then you can.
Okay, I think gallery view would be the best, or maybe no.
Yeah, I will. Who should I make it host now? Shiza or Hania?
Ani is fine. I think this is good. You and Dr. Shabir at the forefront, and
Okay,
I can
I
host.
will give Hania. Hania, now you are the host, the chair of
Okay.
ISWA. You are the host now.
You have to say 1, 2, 3, okay?
Yeah.
So, it's okay right now. We can only, or do you want to change the settings?
No, I
You
think this
can.
looks good.
Somebody
can
said
set
gallery
it-
or something like that. I don't
Yeah,
know.
exactly.
I'm hopeless.
Let's
see
do
us-
both. Let's
to
do
see
both.
us-
One
to see
with this
as
setting
many-
and one with gallery
Yes.
setting.
For
Yeah.
now, 1, 2, 3. Okay, that's the one. And
Yeah.
for the other ones, Shiza, can
To
you
see
help
us-
me?
Yeah, I have done it in the gallery setting. Okay.
I don't see, like, should it go to the other settings?
Now we have the gallery setting view already, so you can take the
Mhm.
picture.
I will say 1, 2, 3, and you can take a screenshot. Okay, yeah. Okay, then 1, 2, 3. Okay,
Perfect.
done.
Thank you.
Thank you. That
Thanks
was a
to
very good
everybody
idea.
also. Yeah,
Refreshing.
please share also with me.
You
I
will
would
do.
really
Thank you so much.
appreciate. Yeah.
So we appreciate Dr. Gheewala not only for the slides, but also for the suggestion to take the social picture.
Yeah, you can
And
share
if-
it also. Yeah, so on the media, I'm very happy to.
So since everybody is agree on the picture, we will use it also for our networks from our size, and everybody is could feel free to use it for scientific and social publications. So now we are concluding the first presentations and starting with the next one. The next presentation would be from my colleague at our team. She just completed her PhD on this life cycle assessment topic in Italy, and it's now time to collect all the details from Dr. Gheewala and put it in a specific context. So Sarah Basi will discuss the use of life cycle assessment in the context of bio waste or compost. She will also give an overview into the software. We have just heard from Dr. Gheewala, different softwares. She will also give a very short overview into this. And at the end, as mentioned, we have another questions and another discussion session for 15 minutes. Then we will go into the break. So Sarah, you could share your slides just to make sure the system functioning now.
Yeah, good morning, everyone. Just let me see. Okay. Now wait a second. Just a second.
Yeah, we could see your slides, but not anymore.
Advance, yeah, screen. Okay.
So some
Yeah.
people are asking in the chat group till Sarah is sharing her screen about the presentations and the link of the today's session. You will receive the link of the today's session recorded, as I mentioned, with the questions remain to be answered. So this is one of the questions I see and listen very often in the chat box. with this, I will give the floor to my colleague, Sarah. Sarah, you
Okay.
could start. But the slides, could you put on the presentation mode?
Yeah, sure. Can you see though? Is it
We can see,
visible
but
or?
this is not on the presentation
Yeah,
mode.
I will, of course.
Okay,
Just
can
a
you,
second.
so I will confirm it, then you can start.
Just a second. I have some
Yep.
Okay, all good?
Go ahead.
Okay. Hi, good morning, afternoon, evening, everyone. I don't know where you're based and connected from. As I was rightly and kindly introduced, I'm Sarah Basi. Nice to meet you all. And I just concluded a PhD on one of the many applications of the LCA, basically on the waste and waste management systems. And so today we will go through together. I will start with some principles just because maybe it's useful to always double refresh some basic knowledges. But of course, let me know if it's still, I mean, are the same information that they were provided in the previous section, so we can directly skip it and go to the case studies. So basically, the very general agenda for today for this session, it would be, as said, some LCA principles, just to refresh some few things, and then we will basically learn how to try and how I used the principles and so the knowledge and the theory on LCA on 2 specific case studies. The case studies are about the organic waste, and the other one is about the municipal solid waste. They are 2 LCA studies that I have developed during my PhD. So, of course, the level is from a PhD student, but the first one was also like we managed to publish, and you will, in case you are curious and you want to go deeper, there is also the link to the scientific paper, and the second one we are still on the process to publish it, but it was already presented in a ISWA conference, so it was already present somewhere within our group. Okay. I simply want to use the pointer, just a second. Can you see my pointer? Sorry, because I don't see any faces, any names.
We
Okay.
can see it now.
So, sure. Okay. And please let me know if all of this knowledge and principles were already explained before, and if you want me to skip directly to the next topics. Otherwise, I generally like to start talking about LCA, starting from the very life cycle assessment. I see someone drawing. Okay. I generally like start to talk about LCA by starting on the life cycle thinking, which is basically the main umbrella within which all the life cycle assessments belong to. Because of course we generally talk about LCA when we more generally think and relate the assessment to an environmental context. But of course, we have now the tools and the knowledge in our scientific community to use it also in the economic and also the social context. And all of these aspects belong to the general umbrella of life cycle thinking. So as you can directly imagine, the life cycle thinking, it was simply a new concept, a new approach developed decades ago that is basically is basically about going beyond what is the traditional focus on our production systems models that basically include the whole looking at and calculating the whole impact related to the full life cycle of any kind of product systems, operations and whatsoever. So I would say that the 2 most important characteristics of an LCT, so a life cycle thinking, it would be being a very holistic approach in which when you want to assess one single impact assessment, I mean, if you want to understand what would be the impact of a specific product, it allows you to do that by avoiding the so-called burden shifting problems, in the sense that before this life cycle thinking introduction, we generally used to maybe calculate the environmental emissions on one specific context, for instance, like how much this process produces CO2, and so how much is the carbon emissions and the carbon dioxide. And the main error, the main mistakes, it was that while trying to fix that specific impact categories, we could fall into the case that we would have created other problems somewhere else. And this is the good part of the LCT, because of course it includes all the different impact categories together without falling into the big mistake of generating errors while trying to fix somewhere else. So it's a very holistic approach. As I was saying before, it is also a great tool because, of course, we can talk about social impact, economic impact, and environmental impact through different assessment, of course. And so it tries to somehow respond to the overall and general more idea of how we should assess something that is very much sustainable in all the three different matrices. Here, just very quickly, as I was saying before, the life cycle thinking is the general umbrella, and under this, we have the social life cycle assessment, the life cycle assessment, which is more, you need to think about the life cycle assessment as an environmental life cycle assessment and the life cycle costing. I wanted to also mention these different aspects of the LCA because we will also see them in one of the two case studies that I have presented today. Going on, I wasn't able to join before in the previous session, but probably all of those very important frameworks were already presented. Just to give you an overview, basically, just remember that the LCA it's regulated by an international ISO. And of course, on an international level, we have two ISO, one on the principles and frameworks and the other one on the requirement and guidelines. Of course, I'm based in Europe. I generally need to use and apply an LCA also responding to the European regulations. But I think there is an international audience, so we can only stick to the international level, which is for sure one of the most important because, of course, it's the most general one. I see some drawing. I don't know if it's only me or someone else sees these green things around here, but yeah, if is it all visible for you, I can keep going.
You can keep going. If you receive the slides and there are some lines on it, this is not from our side, from that person you have to find.
Okay.
Go ahead.
Yeah, sorry for that, but yeah, the most important thing is anything is visible for anyone. So, okay, good. So basically, the life cycle assessment is nothing else that basically calculating the impact of the link that links basically the input to the output of a specific product development. So this is something that we should keep in mind, that basically when you are in front of an life cycle assessment development, you need to imagine your systems as that embraces two different systems. The product system, so it would be the very much the life cycle of your specific product. I don't know, like a bottle of water that has been designed. Then there is the raw material supply, then the manufacturing, the distribution, the use phase, and the end of life. And of course, this life cycle will have impact in the environmental system that is our Earth, basically. And so the link within the input stuff, materials, energy, water, and air that are needed to produce our product, and the link to the output that this product production will generate, to calculate those impacts, of course, we apply a life cycle assessment. So it is basically our tool to connect the product system to the environmental system. I'm sure you know about this, that the life cycle assessment is an iterative procedures, let's say. So, and it consists of 4 different steps: the goal and scope, the inventory analysis, the impact assessment, and interpretation. Saying that it is an iterative step, it means that maybe you get to the interpretation step, you realize that there are some mistakes, some discrepancies, or simply something that it cannot be 100% really comparable with other kind of studies. So you simply need to go back to your goal and scope, maybe redefining the goal, or maybe you simply realize that you made some mistakes on the inventory analysis, or potentially also on the impact assessment too. is based on a very linear mathematics behind. We don't need to know what there is the mathematics behind, but just keep in mind there is a very linear modeling. There is nothing too much complicated behind. The most important criticality when we deal with the LCA and life cycle assessment is just like the amount of data and the gathering of the data. But besides this, it's not a very complicated tool to use. Okay. So we said that we have 4 different stages, so 4 different steps, and of course each one has sub-steps. So at the beginning it might seem a bit overwhelming to develop all of these because you don't, I mean, there are a lot of things to assess before running the LCA, but when you get used to use it, you will see that maybe you can the most important part, of course, it would be the inventory analysis, that is basically your data, the input and the output, and the impact assessment, that it would be the calculation of the impact between the input and the output. The goal and scope definition, we will look at that a bit closer right now, and the interpretation too, it would be simply interpreting your results from a critical point of view, as you are generally doing any other kind of assessment, but is generally what we generally do is to run maybe some sensitivity analysis to see if the results that we obtain have make sense, basically, and also maybe if we want to change some data behind, you will basically understand through a sensibility analysis if by changing the data your results will be affected. This is something that is generally done. And then, of course, you will get with some final improvement and also some comparison with already published or maybe already other kind of studies that maybe had your same goal, your same data, and then of course it would make a lot of sense to make some comparison to see also the reliability of your assessment. But going step by step, what about the goal and scope definition? The goal and scope, they might seem something that it's a bit like a synonym, but they are not in this context. With the goal, simply we mean which is our goal of the study, and our ISO standard, they help us on structuring the goal of the study by providing us 3 key questions. And so when you want to develop the LCA, first of all, you need to ask to yourself what I want to assess, why, and who is the audience. By answering these 3 questions, you will have your goal correctly framed, let's say. While, what about the scope definition? The scope definition is a bit more tricky because it's basically a list of different indicators that you need to choose before starting the whole LCA. I'm sure you went through all of this already, so I will be very, very quick, but of course, keep your question to the end of the session, so we will try to fix anything that it wasn't clear. But I selected just some of them because of space and time, of course. But let's start with one of the indicators within the scope stage, which are the system boundaries. The system boundaries are, we have 4 different, of course, let's do a step back. We said at the beginning that the life cycle assessment is something that it has an holistic nature. So it's able to look at the whole picture of any kind of production. But of course, depending on the goal, depending on the audience, and also depending maybe on you want to develop a comparative LCA, you might end up in the situation that looking at the full picture is not 100% necessary, but you want to maybe specify something that it's a bit more on details. And so the ISO standard provided us also the opportunity and the options to basically divide your study into 4 different options. Like you might run a cradle to grave LCA analysis, or which means cradle to grave is the most complete one because it goes from the very resource extraction, let's say, so the raw material supply until the very end of life of that material. There is also the option to make a closed loop, but I think that the scientific community it's not sure how the closed loop is 100% representative and is 100% correct when we are in front of this kind of LCA, which is because of course it's different from a circular economy assessment. But in case you also might choose to go from a cradle to cradle, so closing the loop of your production and your life cycle. Then there is the option to use a cradle to gate, which means basically from the raw material extraction until the end of the production stages. Maybe because it happened to me to use this kind of option many times, because maybe I wasn't interested in assessing the use phase, the disposal, but I was very much interested on the production of one single product and how this production might affect the overall environmental impact. So using the use phase and the disposal would simply somehow complicate too much my system. Then gate to grave, it's simply like going from the end of the production until the end of life. And gate to gate, it's simply, of course, assessing the production itself without maybe even questioning too much about the raw material extraction and, of course, the end of life. The functional unit, it's maybe the most important thing on the LCA, because, of course, we are in front of a calculation tool at the end of the day, but we need to calculate many things, which means that a lot of data that we will include in our LCA are measured through different unit of measures. So, of course, if you want to calculate a system and not a single indicator, let's say, you have so many units of measure that you need to come up with one single unit of measure to make the assessment calculable, let's say. And so what they did was to structure and invent this functional unit that, as the name suggests, refers to the function of that system that you want to assess. And so basically, because maybe in your data you have something that is measured in meters, something else that is measured in liter, in kilowatt, whatever else of the unit of measure. So this is the reason why the functional unit was used. But how to decide which is the functional unit used that you need to use during your assessment? Here again, there are some questions that helps you to somehow address all your point and to come up with a very structured functional unit. And so it's always good to understand what is the function of my system, how much will this last, for how long, where do I need to apply it, and how well. Here we have a very basic example of a t-shirt that, for instance, you might use a functional unit as one t-shirt is my functional unit to assess the life cycle assessment of one t-shirt. It's fair enough. But if you want to be more detailed, and more detailed you are in this stage, the more you will be able to assess the results during the interpretation stages, then you might also come up with a functional unit that is able to answer all of those questions. So I want my system to have a functional unit that is one t-shirt, so a t-shirt, one t-shirt, just one and not 100, for instance, that is wear 1 time per week and is washed through a washing machine at 30 degrees. And then that is going to last for me for 5 years. So more details, more information you have at this stage, the more will be easier for you to calculate the impact assessment, but more importantly, interpret the data you had. Just to give you another example, as I was saying, and you will see now in a second, I generally use the life cycle assessment in the waste sector. And so the waste sector is something that is not a production, it's a system in the end of the day. It's something that is more on a general terms. So the functional unit that I generally use is, or maybe 1 ton of waste that is generated. And so with 1 ton, I have something that is a single entity. It can be easily compared with other study. Or what I choose generally is also like the amount of waste that is generated in a year, in a city, in a recycling plant, in a composting plant, or whatsoever. So the functional unit should be something that you should choose it in a way that make your life easier through the LCA later on. Okay. Here, I think we can skip all of these technicalities because otherwise it's going to be too long. Then the data quality requirement, this is obvious as any other kind of studies. Of course, the data here are the most important things because you might end up working with a bunch of data, tons of data. And of course, it's not just about the quantity of the data that you are able to collect, but also about the quality. And as many other kind of assessment, we differentiate the data quality in three different, let's say, categories. You have primary data, where you are able to collect first-hand data, which is quite hard because, of course, industries, companies, whatsoever, they are not that fine by sharing private data. It's obvious. But if you do that, that would be the best because, of course, your LCA is 195% reliable. Secondary data are simply data that they come from literature, but more often from databases, and they are they are quite largely used. Or tertiary data, they are just average data, but I do not recommend you to use it fully, but just maybe to assess some data gaps. Just to make a link with what we were saying before, simply measuring the quality of the data that should reconstruct all of your systems. So the foreground system is basically the system that it's describing your life cycle of that product that you are assessing, while the background system is something that basically is the link between the life cycle of the product with the environment outside. So on a general term, we say that for the foreground system, it's always best to use primary data because, of course, it's the focal point of your study. And for the background system, so it's what your production will be linked to the outside world. It's still good, of course, to use database and secondary data because they are obviously reliable, but it's not that needed to go too much into the first-hand data because it would be impossible otherwise. The impact assessment, I entered the very last 10 minutes before in the previous section, and I saw that you were already going through all of that. Basically, this to measure this link between the input and the output. And so the impact assessment, we have different methodologies. And according to the methodologies, all of these select different impact categories. The impact category list is somehow summarized in this table with the unit of measure, where does it come from and how it was assessed. But this is something that it goes way more in details and is not needed for now, but just keep in mind that generally when you run an LCA, you will obtain results that speaks in terms of climate change potential, ozone depletion, eutrophication terrestrial or aquatic, land use, water use, and so on and so forth. Yes. Yeah, these are the midpoint impact categories, and are the endpoint impact categories that are on a more general and final impact assessment. Here is just an example. In the case this slide will be shared with the audience, you just have an example of how in a, for instance, scientific paper, but this is also works in a report, in any kind of publication and writing, how to describe a goal definition, how to describe the functional unit that you selected, and how to describe the system boundaries. No need to go through that together, but in case you have also an example from a specific paper. The inventory analysis is nothing more than an inventory. So it's simply like linking the input with the output. And so in input, in any kind of production, we will have raw material that then in the output, they will be turned into a solid waste. Then we have the energy that, of course, will produce air emission, for instance, and the water that will produce water emission. Of course, to somehow the errors represents the impact that the production will have, and we will be able to assess it with our impact categories. In terms of life cycle inventory, as I was saying before, this is, of course, is the inventory of all the data that you need to collect. And as I was saying before, you might choose to go for a first-hand data. Otherwise, you can use secondary data. And when I say secondary data, generally speaking, we refer to databases more than literature, because databases are a bit more reliable because there were many years of assessment to come up with that specific data. And here there are not all, but many of the databases that the LCA practitioners used. I'm very much used to use the EcoInvent database, and because it's one of the most larger one, but also one of them that is like more often updated. So the data that you find there are pretty reliable and also recent. And it is the database that it is used from many softwares. We will see that afterwards. The data impact assessment, you saw this slide just before between the mean point and the end point. Nothing to add from that beautiful explanation that the professor has already provided you before, but simply just this is our two different kind of impact in our world. If you generally, we present the results at midpoint simply because are more specific, and also because it's very hard to get this data here. So of course, when we present the results, we are always speaking in climate change potential, human toxicity, specific cancers, non-cancer, respiratory inorganics, all of. But just think about the endpoint as the more general impact assessment that groups together different midpoint impact categories. What about the impact category step? You have 4 different steps. 2 of them are mandatory for sure. Which are the red ones, the classification and characterization. And then there are 2 that are optional, the normalization and evaluation. I generally stop here at the characterization because I simply like, I found it a bit more easy to compare with other study. On the normalization, it's a bit more tricky. Anyway, the classification is nothing else that basically classifying for each of the LCA result from the inventory that you obtain, giving it a specific impact category potential. So for instance, of course, carbon dioxide, methane, they all belong to the very bigger umbrella of global warming potential on a qualitative base, and this is the classification step. Then if you want to translate it into a quantitative step, then you need a characterization step. This is just on theory. On practice, unless you are not doing that on Excel, you don't need to know all how to move from the classification to the characterization through characterization factor, because there are the software that do that for you. Just you need to know it because, of course, the more you know, the better you are able to of course, read and interpret the results that you obtain. I'm sure you went through all of this together before, so I won't spend so much time here. I simply maybe want to make this example because I think it's quite explicative on the characterization step that, as said, it is the quantitative translation of the classification phase. But and to do this translation from the qualitative stage to the quantitative stage, we need a factor that, of course, tells us how much that specific emission affect our results. And so they have listed, the scientific community listed the characterization factors for each of the impact categories that will be used to do this translation. But just let's have a look at this example here, that methane is a greenhouse gases with a higher impact than carbon dioxide. The impact category, global warming, which both methane and carbon dioxide belong to the global warming impact category, and this impact category uses a reference of kilogram of as a reference, as a unit of measure. The global warming is assessed and calculated in terms of kilogram of carbon dioxide equivalent. And the characterization factor for carbon dioxide is obviously 1 because it's the same as the reference unit of measure used for the global warming, while for methane it is 25. This means that 1 kilogram of methane is the same as 25 kilogram of carbon dioxide in terms of life cycle assessment, simply because of the characterization factor that describes the single greenhouse gases in this case. The interpretation results, as said before, there's nothing more than, it's a very long process, but I'm sure you went through this already. But basically, the interpretation is just identifying the most significant issues based on the results that you obtain, and then evaluating them and consider the completeness and the consistency of the study. You simply need to do data gaps filling, or maybe you need to, again, run a sensitivity or sometimes also an uncertainty analysis might be useful. And then, of course, come up with some conclusion, limitation, and recommendation. I generally run a sensitivity analysis also to compare my study with something else by changing some data at the input or the output, also to see how the system changed according to the data that we included. Anyway, for more info, I have included all the references in each of the slides and also at the end, so in case you can also have a more complete look at this. The LCA software, basically, this is just some of them, because I think I don't know all of the software that are generally used in LCA, but for sure those ones are the most used right now currently. This was a paper on from some years ago, but it's still, I think it's something that is still accurate. The most used the most used software is CIMA Pro, this one, and it is the same software that I was mentioning before that is that uses the EcoInvent database to run the results. Then there is, for instance, the Easy Waste, EastTech. It's a software developed from the DTU, the Technical University of Denmark in Copenhagen, and is largely used not for all the kind of contests, but more particularly for the waste sector. Then Gabi software is another quite used software, but I'm not a Gabi user, so in case you have any question, I don't know, because I generally use CIMA Pro and EastTech. There is also OpenLCA that also is very nice because allows user to run an LCA without having a license, because it's a free software, it's for free. And then there are many others that are that came out also during these past years, because of course the LCA became a big thing. But anyway, this is a paper that it was a review of all the different software use in literature, the impact categories that are more frequently assessed, the kind of data that are generally, I mean, it was for each of the single steps of the LCA, it made a very, very intensive review of what is happening in the world around the LCA. So if you are curious, I suggest you to read it. I think with that initial part we are done. I can move to the case studies that are a bit more maybe interesting, and we also can see how this can be translated in a practical term. Since those
Sarah, sorry for interruption. You have a bit more than 20 minutes.
More.
22 minutes you have exactly.
Yeah, of course, I can make it, because the introduction was the most, it was the longest part. Sorry.
Good.
Okay. Thank you very much. Okay, so the two different case studies, as I said before, are something that I developed during my PhD. So here I simply reported the title of my PhD because somehow also summarize what I have assessed. And it was basically waste management systems between Europe and Latin America, a life cycle thinking approach. So I have brought here today one example from Europe and one example from Latin America. Okay, the first example and case study is, as I was saying before, if you want to read it, there is the DOI here, the link, and so it's on organic waste, and the title is Plastic Impurities in Bio-Waste Treatment, Environmental and Economic Life Cycle Assessment of a Composting Plant. So basically what we wanted to assess, it was, of course, the environmental impact of the composting plant itself, but the real goal here it was to understand how much the plastic impurities that end up in organic waste might affect the environmental and economic performances of the composting plant. Because I don't know if in your countries or if you know that there are plastic impurities in the bio waste, and through this study we realized that of course there are biodegradable plastic ended up in the organic waste, but unfortunately also virgin plastic impurities that end up in the organic waste. Okay, the case study is focuses on a composting plant in the north of Italy, close to where I did my PhD. They are just, I think they just produce compost, not any biogas processes. So we didn't assess that, also because we were very much interested of the consequences of the plastic impurities in the compost. So something that will be used by citizens and by industries. This is nothing LCA related, so I will be super quick, but simply to understand and to calculate these impurities, we started by a plastic characterization and a waste flow analysis. And through that, we were able to understand how much biodegradable and virgin plastic were ended up in the bio waste, and so before the composting process. And also we calculated after the composting process, also to see obviously the degradability potential between the biodegradable plastic and the virgin plastic. And by doing so, we came out with this very final table on this initial section on the plastic characterization, thanks to which we realized that, of course, biodegradable plastic almost disappeared from before the composting and after the composting process, while plastic, virgin plastic, they almost stay the same between the initial and the input and the output. And so, of course, we could confirm that they are an issue, obviously, that's clear. Then, of course, we ran an LCA because we wanted to understand the impact that these impurities had. And so here I simply reported the initial slide that we were looking at before, simply to show you that in this specific case study, I have used the slides change automatically. I have used the environmental life cycle assessment, but also the economic life cycle assessment. We weren't, I mean, to run all of these LCA, they are very time consuming. So initially, we wanted to assess also the social part, but for the scope of this study, it wasn't the most focused. It wasn't our focus because, of course, it had consequences, but the most critical aspect was the environment and the economy, because, of course, then it changed the benefits and of the composting plant if the compost that they obtain it's good enough to be commercialized, or if they need to run so many additional steps to get rid of the plastic impurities that they found in the beginning. Okay, let's start the LCA part, just looking at a flow chart, basically, that the plant, what they do is basically collecting food waste from households, but also from offices, I would say. But together with the food waste, what they do is also collecting food waste, so the whole organic, the bio waste that you are able to collect in a city. And together then through 3 larger steps. Of course, we also had sub-steps, but I simply reported here a more simplified diagram that basically the LCA included the waste transportation step, then the shredding and the mixing and the maturation of the bio waste, and then a screening phase through which they were able to obtain at the end a compost fraction, let's say, but also together with this they obtain wood waste that is generally reused into the process, so they tend to not waste any wood, but it's just like rerun and make closed loops. But also there are some solid waste that are generated from this process, and so of course they need to be sent to a solid waste treatment. Of course, here just to make a link, our goal and our focus were the plastic impurities. So of course, on the output perspective, what we wanted to look at and make a comparison and some interpretation, and so some comparisons and assessment was the solid waste treatment, because it was the step that in case needed to treat the plastic impurities that are found in the organic waste. As you can see, we have a dash line here, the black one, and this represents basically the boundary, the system boundaries. In this case, again, what we did, it was a cradle to gate, in the sense that we didn't assess the use phase and the selling phase, and so also the final end of life of the compost itself. But we were only, for that study, maybe we might think of also assessing the use phase because it might be interesting. But what we did, it was only like starting from the initial waste collection until the end of the production of the compost, and so the generation of the solid waste. The functional unit, as I was also trying to more or less introduce to you before, in this case, it was the total amount of food and wood waste delivered to the facility in a year. This is the functional unit that we chose because it was easier to use this functional unit. It was well representative for the overall system. But then you will also see that in order to run a sensibility analysis, we also translated our results in something that it was more comparable, which it was our results into 1 ton of waste. And so by making this translation, we were able to compare our results with other literature studies to understand the references. Cradle to gate analysis. Okay, we can go on. This is just a section. I think it's not all of the. I wasn't able to include all the data that we had, also because some of them were a bit confidential and they are not even in the paper. Anyway, this is a life cycle inventory. And so, so this is basically a list of data that you need to collect in input and in output. What we also did, it was what I like to do generally to make my data collection a bit tight, you know, and also very clean to then be able to use it more correctly in the softwares, is to divide in the data collection into the steps. So the input, we collected data on the transportation step, then the input on the shredding, the mixing and the maturation, and then the output data on the specific screening, on the specific shredding and mixing and maturation, so having the input and the output, and then at the end reconstructing the screening and the waste treatment again between the input and the output. What I have highlighted in red are the plastic mixture that of course were obtained as solid waste. As I was showing you before, besides the compost production, we also obtain solid waste, and some of them are, for instance, metal waste, glass waste, textile waste, and the plastic waste. And then of course all the paper was structured in a way that we wanted to play around this plastic mixture that was found at the output at the end of the system. This is just an initial results, and as you can see, our focus was very much on the waste treatment. And so if you look at the different impact categories that we assessed, you might realize that the waste treatment had the larger share in most of the impact categories, for instance, global warming, freshwater aquatic ecotoxicity, but also human toxicity, and basically because of the plastic treatment. And so what we wanted to see now, what we wanted to look at later on, it was to basically compare these specific results to a scenario analysis. And the scenario analysis, it was something that assumed that no plastic impurities were found in the organic waste, and so no plastic treatment were needed to be assessed at the end of the production. And by doing that, we basically realized that the waste treatment decreased quite largely from here to this kind of graph, if you look at the green histograms. And so, of course, we could somehow prove that the plastic treatment, it's an issue in this kind of context because of the safety of the compost, okay, from an human health perspective, but it's also an issue when it comes to waste treatment impact in most of the impact categories that we generally assess. Here is just, for instance, the comparison between these different scenarios, so the baseline scenario and the scenario analysis, and these are the percentage of reduction when the plastic impurities are not present at all, and so they don't have to be treated at the end of the systems. And this was possible to do it just because of the LCA assessment, obviously. Otherwise, it would have been too much difficult, I would say. Then, as I told you, we also try to assess life cycle costing. So looking at the overall picture from an economic perspective, because of course I mean, generally you need to deal with industries, with companies, but also if it was like a specific product, anyway, the environmental aspect when you want to run an LCA I don't know, for any kind of production, of course, this has also to be beneficial from an economic perspective. And here our goal was the same, because when you want to run this kind of different assessment for environmental, social, and economic, what you need to keep constant and the same, it's obviously the goal, so that you might look at the same story from simply from different perspective. I won't go too much into the details on that part on the LCC, because it's totally another sector. And also I'm not an LCC super expert. I just use it a few times. But just keep in mind that there are different types of life cycle cost. There is the conventional life cycle cost, the environmental life cycle cost, that is not the same of the environmental life cycle assessment, but of course it has a lot of similarities, but it's an economic assessment. And then there is the societal life cycle cost. What we used in this study on the organic waste, it was the societal. So this one that takes into account the external costs, the externalities, and also the impact on the social aspect. These are the results of the life cycle cost from the baseline scenario, where the plastic are present and they correspond to around 7% of the overall cost that the plants needs to pay at the end of the composting treatment. And these are basically the results from the life cycle cost of the scenario analysis, where the plastic impurities are not present, and so the plastic treatment is not measured because there are not, but only biodegradable plastic. And of course, the 7% basically disappear, and overall, the total cost that the company needs to pay annually reduced. Great. I think we can move to the last. I'm just checking the hours. Okay. To the last case study. It would be a bit quicker because it's many things we have already touched. But this, here there is a mistake. It's not organic waste, but it's municipal solid waste. Okay, this it's a study that the title is Environmental Profile of the Informal Waste Sector and Source Segregation in Waste in Municipal Solid Waste Collection in downtown Lima. As I told, it was something that it was already brought and shared in a conference, but is not yet in any scientific publication. We are still on the process. So here, basically, what I wanted to do is to apply a life cycle assessment, not to a facility, a company, a specific production, but to the waste management of a specific city. I won't go any details why we choose Lima, why there is simply within my PhD, we wanted to look at the European framework and Latin American framework because of a collaboration, and we chose the capital of Peru, which is Lima, of course. This is simply because when we talk about waste management systems, this sector drastically change when changing the countries and the geographical areas. that this is nothing new to anyone. It's simply in a, I would say I don't know, in Europe, generally, we have something that it's a bit structured because of the directive, because of the legislation and so on. So there is a collection, waste sorting, and then there are many end-of-life solutions according to the sector. So the waste to energy, landfilling, but most likely the recycling process. In most of the geographical areas, all of this structure is not present at all, but what happens is that the waste are, if they are collected, they will be simply left or undisposed in streets and so openly dumped, or maybe there is the landfilling solution, and so the sanitary landfill as the only option. I wanted to run an LCA in this kind of context because I found that it was quite interesting also to look at a system that it was so different from what I was used to, but especially because from an LCA perspective, I wanted to understand the link between the collection of this kind of city that on one end there is totally formal, on the other end there is the informal collection. And so how these two flows speaks to each other on an environmental in terms of impact categories, and so in the overall general framework of the LCA. Next slide. I cannot change. Just a second. What happened? Okay. Yeah, this is, we can skip it. It's just a literature review to start the study later on. Okay, here is just of course, in order to run an LCA, this is applied for anything, for a company, for a product, for a system. You need to understand the system and the context that you want to work with. And so, of course, I needed to do some research on the waste generation, the magnitude, and obviously how the waste assessment worked in that context. And in this case, we are in the case of Lima in Peru. But this is nothing that we are not interested right now because we want to talk about LCA only. But this is just to say that before running an LCA, make sure that you have a very good understanding of the things that you want to assess. In this case, it was the waste management of a specific city. So the main objective of the project, it was to understand the environmental profile and the derived challenges, of course, and opportunities that are related to this dichotomous characteristic of the waste management system in Lima, the formal and informal waste flow. To understand this environmental profile and challenges, of course, my tools was the LCA. How did I use it? I, again, starting by choosing the functional unit, and in this case, again, was the total amount of waste generated in the city of Lima in 2019, because I went there in 2022, and 2019 was the last year available before the COVID pandemic, so it was the most representative one, let's say. Then the impact assessment method that I used, I'm sure you have seen this impact category assessment method, the methodology before in the previous section. What I generally use, depending on the case study, but in this case, I use the RECIP midpoint impact assessment simply because it was the one that provided me with most of the impact categories. So I could be able to look at the system from many perspectives. So in terms of climate change, ozone depletion, terrestrial acidification, and so I could have the most general and complete overview of the story. The software that I used was the ISTEC, as I was somehow trying to make you understand before, which is the same software that I was mentioning that was developed by the DTU, and simply because it's largely used and correctly used when it comes to waste and waste management. This is it was my system. The dashed line is simply the system boundaries. In this case, again, I started, it was a cradle to grave, because I considered the wasting input, then anything that happened during the collection, the transportation, and the landfilling option. And then, of course, what I didn't, I also include in a scenario analysis the recycling aspect, but this was only for the scenario analysis. Otherwise, my system ended at the gate stage, and so at the end of the treatment of the waste without any circularity, let's say. As I was saying, simply just to give you an overview, and so we can then look at the LCA results a bit better later on. How does this system work? Basically, in Lima, the waste are first, once they get generated, they might undertake 3 different directions. They might get formally collected, then transported in a transfer plant because of long distances, and then they will be simply left and disposed of in sanitary landfill. Otherwise, the other flow is the informal collection, and it is obviously transported and brought to a collection point. And thanks to the informal collectors and recyclers, those waste then will be likely recovered and recycled, and then the granules, let's say the polymers from the plastic or whatsoever, they will be sold to industries or to citizens. So if a recycling option happens, it's only because of the informal flow, at least in this kind of city, in this kind of context. I cannot talk on a general terms. The LCA has to be very site specific and study focused. You cannot generalize when you talk about LCA because you have results that are strictly dependent to the context to which you apply the LCA. So this is only on what I have assessed in this context. And then, of course, if the wastes are not informally collected and then transported somewhere else, they will be unlikely just left undisposed streets and openly dumped. And so there will be some waste degradation simply left around the cities. Here I went a bit more specific on the different flows that this waste might undertake. It's not needed for us to go into the details on that. Just keep in mind that the formal flow on a LCA perspective needed to include the collection and then also 2 kinds of collection, because of course there is one trucks that collect the waste and bring it to the transfer plant, and then there is another truck with another tonnages whatsoever that brought the waste from transfer plant to the very end landfilling activities. And this is because I want to make this remark simply because in the waste sector, when you apply an LCA, the transportation step, so the collection plays a very huge role because it's most of the impact categories that is generated besides, of course, the end of life. And on the informal flow, this is the recycling workers dynamic in Lima. So we have many informal workers and waste pickers, and each of them has specific tasks and duty, but this is not the topic for today, but simply this was included simply to show you that the LCA was used also to assess this kind of dynamics. And then the critical hotspots are simply, as I said, the waste that are not collected and so left in streets. Okay, what about the life cycle inventory? So our input and output collection. This is just like some of the inventory that I consider because of lack of space of time. But anyway, again, I follow the same structure as I was showing before. I generally start by including the input, the output for each of the steps of my system. So in this case, from the generation step, then the waste segregation and sorting, then the collection and transport, and then the end of life. And what about our results? This is just an initial example of the baseline scenario. And from these results, as I said, I use the recipe methodology, so I obtain results in terms of many impact categories because I wanted a complete picture. And as you can see in this kind of context, the landfilling, which is the red section here across all the different impact categories, is the one that basically has the largest shares in most of the impact categories, besides the terrestrial acidification that is basically largely generated because of the informal collection. I'll explain you why later on. And then the formal collection, of course, has also some impact because of the transportation, but nothing compared to the landfilling. So we can still highlight that landfilling and end of life, it has impacts in most of the impact categories that we want generally to assess. But what about applying some sensitivity analysis in this case again? Because what I was showing you now, and so providing some contextualization and looking at the results, is already an interpretation stage. And so within the interpretation, of course, we need to also try to look at the results a bit more critically. And so what we generally do is to run some sensitivity analysis. And so think about other kind of scenarios that might change the structure, and you also look at something that might improve the system and the impact and the impact of the system that you have obtained as a result. In this case, besides the baseline scenario, which is S1, I have run a couple of different scenarios. S2, it was simply a condition in which the recycler work, so the informal sector, is implemented by 15% more, both in the collection but also in the recycling. While the third scenario refers to a condition in which the recycler's work is not present at all, and this means that the waste collection is completely managed by the formal collection, and so of course by this section here under the one category. Great. And so if we run the results comparing the different three scenarios, this is what I have obtained. So as I said, I ran the results for all of these impact categories, so there were too many. I simply included here an example of 3 impact categories because I found them a bit interesting to look at because they really report in different outcomes. And I selected the climate change, the terrestrial acidification, and then the fossil depletion. For all of this, I have displayed the results for each of the 3 different scenarios. And so if we look at the climate change, we can see again that the landfilling plays the most large share and basically has the highest environmental impact across the 3 different scenarios. So it doesn't matter that much if we change the scenarios and the condition, the landfilling in terms of climate change is still an issue. Of course, the second scenario is the one that probably performs better because we have some positive outcome, because of course, I'm sure you have already realized, but I like to present the LCA results in this way, but if you look at the graph, these are positive values, and so they correspond to a negative impact because it means that there is an impact. Then here we have negative values, so it means that we have a positive outcome, and so if we found here the paper recycling that it's below 0, it means that it had played a positive role in the overall environmental impact of the system. What about the terrestrial acidification? In this case, the third scenario where the informal collection is not present at all, it seems to be the one that performs better because it seems that we have very low results, but simply because one indicator is totally missing, but it is feeding the formal collection, because as I said, what was happening in informal flow in this case was basically all the waste were basically collected formally, and so brought it to the landfilling. But in terms of terrestrial acidification, this was the ones that perform better. And if you want to do some critical review, you can also see that this is somehow corresponds to the initial results that we obtain on the baseline scenario, because on terrestrial acidification, we had that the informal collection played the largest role. So if we delete this indicator and put basically the input into other indicators, then we have the environmental impact decreases, again, all in terms of terrestrial acidification. What about the fossil depletion? And then I can conclude my presentation and my talking and give you maybe the words to you. In terms of fossil depletion, in this case, I found it interesting to present it here, simply to show you how a positive outcome in terms of LCA look like. And here we have, for instance, the paper recycling, that it's something that basically has a positive outcome. And so the second scenario is the one that performs better in the end, because of course there are a lot of environmental impact from other indicators, but there is somehow a balance that provided us a situation in which the overall environmental impact it's better and is improved. So if we are, for instance, a consultant people and we want to assume that we want to tell to the municipality of Lima how they might change the waste collection system, the waste management system, we will be probably present this kind of results and telling them, I don't have a correct answer, because in front of an LCA there are always some doubts and so many indicators to take into account. But look, that if we want, for instance, to improve in the fossil depletion impact, I would say that you should work you should focus on the second scenario, and basically this means that probably a solution it would be to improve the informal collection, because of course this is something that there is a recycling here, and this means that of course the environmental impact decreases. There are, I would say, so many other things to say to interpret, but I think for now it's more than fine. I think I provided maybe even too much information, and I'm here for any questions you might have for me. Thank you very much. I stop sharing maybe, or you tell me what I should do.
Thank you very much, Sarah. As you mentioned last week in our internal meeting, you could even talk about this topic for hours, but you have to shrink all the details and bring it into 1 hour. I know it's challenging when it comes to a PhD research.
Yeah, right.
It sounds like the previous presentation from Dr. Gheewala, you got a lot of questions and attention from our participants.
Okay.
I think we cannot go through all the questions. We need 1 hour. And I'm quite sure you have answered all these questions in your research. It's all about time for now, but we pick up some questions randomly, and we will send you the rest of the list, so you could just give a short answer of the questions for our audiences. The first question is from Haile. It's more about solid waste management. So I would suggest we skip this question because it's not directly related to life cycle assessment. He is asking about different solid waste management scenarios and waste policy in each country. So this is more related to solid waste management, not to life cycle assessment. In case you are interested, Haila, you could just approach us and we can discuss on this. Since I'm also working for a municipal company for a city in Germany, I'm writing my thesis, PhD thesis about similar topics. So this will keep it for now. The second question is from Haula Masmoudi. Why you didn't include emissions in the system boundaries, Sarah?
Can I wait a second? Maybe it's good to reshare the slide.
Yeah, you could. You're free just to share. I wanted to say.
Just a second. Let me see where. Wait a second, guys. Oh.
So I try to pick up the more related. Well, all the questions are related, but some questions we had in the previous session. Just to avoid any repetition from now, we just pick up some random questions, which is new or maybe more related to the presentation of Sarah. Nonetheless, some questions are new, but still we keep it unanswered in this session because of time. And the second reason is some of the question is related to the presentation of afternoon from Fabias Diaz. he will answer many of your questions in the list. I can see it. So when your question is not answered, just stay tuned for the presentation after the break. Sarah, now the floor is yours to answer the question why you didn't include the emissions in the system boundary.
Yeah, sorry, was this case study on the previous one?
It
Maybe
was
we
a question. There is no detail for the questions.
Okay.
You can just
Okay.
feel free to give to pick up an option and give an answer.
Yeah. Yeah, maybe because when you need to speak fast, you miss some points. Apologies for this. Basically, in the paper and in the presentation was, I would say, correctly explained, but for instance, if you look at this graph, anything that is covered by a dash line, it was included in my LCA. So it was included in the system boundaries. But of course, I wanted to differentiate what it is exactly the system. And so let me go to my pointer. So all of these rectangular here, and something that is still included in the assessment but refers to the input as the vehicles, the material, the water and the energy, and what relates to the output, so the environmental emission. It's not that they are not included because it's not written system boundaries. They are, but simply the system boundaries refers to the systems itself. So where the production of the waste, for instance, end, and where, or if you want to continue with the end of life or whatsoever. So where the system of that specific product or maybe any other kind of system basically starts and ends, and the environmental emissions are indirectly always included because they refers to the system boundaries that you selected. I don't know if this was enough clear and if I answered the question, but basically the environmental emission, it doesn't relate to the system itself, it's the consequence of the systems. It's our output that I was basically trying to explain before in the inventory step. So of course this is something that is generated because of this system. And so basically the system boundaries are kind of to gate because we wanted to end them here, but of course they generate those environmental emissions that are included in the LCA.
Paula, I hope that answered your question. The next question from Mariam Khalid. What is the difference between circular economy assessment and LCA, life cycle assessment? Can you elaborate more on circular economy assessment? I'm not sure if you have included this in your research, like circular economy assessment.
No, I mean, at least I didn't include it in the slide. I simply said that when you have this choice on the system boundaries, you might also consider to do a cradle-to-cradle analysis, which means that, of course, it's a circular and a closed loop system. It's possible to do, but the LCA looks at the life cycle that generally has a start and an end, and the start doesn't 100% and always correspond to the end, because maybe we want to go from the raw material extraction until the end of life and how we treat the waste and manage the waste. I'm not an expert on circular assessment, but I simply wanted to make the point during the presentation that when you are in front of a circular economy assessment, obviously you need to look always at the circularity because of the definition of the assessment itself. So in that case, you simply, I think you don't have any choice of not choosing an open loop, but you always need to close the loop, and so going potentially and ideally from the raw material to the raw material again. But anyway, they are, I would say, even two different sectors, the LCA and the circular economy. They, of course, talk to each other because there are a lot of similarities, but there is not a circular life cycle assessment. I mean, it was simply to say that on the life cycle assessment is not often used and is not always something that is even recommendable to close the loop, because it's maybe wasn't even the nature of the life cycle assessment when it was invented at the beginning. Of course, the more you close the loop and the more we have recycling and less waste, less emission whatsoever, but it's a tool, the life cycle assessment, that allows us to measure what happens in reality. And most of the case, this closed loop doesn't happen.
Just to mention, we stick to our program. We are over of time. We take the last question afternoon after the break. So we will still have a discussion session after the third presentation of today from Fabian Diaz, and we will get back to these questions. We have it now. I am just in rush to give you enough time to eat, to cook, to drink something. So the last question we take for today related to the composting production. It is from Solomon. The question is, can we use the same methods of the life cycle assessment for different types of composting production? I'm not quite sure if it's about different models of composting, like tunnel or open window.
Yes. Okay, I would say that this is a very specific question, and maybe it's more depends. I mean, the life cycle assessment, it's a tool that we have to calculate the environmental impact if we want to calculate the environmental context, not the social and economic. So it's not strictly dependent to the context and the sector you want to apply the LCA. So ideally, you can apply an LCA to any kind of sector, any kind of best practices, or any kind of industrial processes and whatsoever. So I would say that, I mean, if it's good to apply the same LCA if we change the composting production, of course it is, but it's also, they are not dependent, because the LCA is our mathematics, is our equation to then calculate the impact of the specific processes. So if you change the processes, the mathematics and equations still are the same, because it's simply something different that it applies to our process to allow us to have an environmental, to basically calculate the environmental impact. So simply choose your process, what you want. I think the goal part, probably the professors before made it super clear. What the goal point and the goal stage is one of the most important, because to the goal that you displayed and disclosed, all the LCA depends on. And so if your goal is to assess the specific compost production, or maybe you want to make a comparison between two compost production, you are free to use the same LCA methodology and impact categories to both of them. But because it depends on the goal and what you want to assess. The LCA is always the same. What changes generally are the impact category. And generally you choose the impact categories, and so the LCIA methodology, according again to the scope, depending on what you want to assess. Maybe I'm interested on only knowing the global warming production because I was tasked to do that, or simply because the industry made a change in the production system, and so we simply wanted to look at the consequences of the production system change in two or one impact categories only, and then you can run an LCA with just one or two impact categories. So I would say it really depends on the goal, and you depend on the production processes and the industry basically. But in terms of LCA, is always the same. It's simply choosing which impact category you want to assess because of the goal and because of the audience.
Sarah, on behalf of the participants and our group from ISWA, we all thank you for the incredible insight into the practical examples.
Thanks to you.
And I hope we get all the answers of the questions from you when we share with you.
Thanks to you guys.
Thanks again. Now, before closing the sessions, just 1 minute from my side to give you an insight. I see many questions on free access lifecycle assessment software or database. As mentioned, we will cover this in the next presentation after the break from Fabian Diaz, and some of the questions will be answered after that presentation. The remaining questions will be also discussed again next week on Monday by my colleague Shiza Aslam. So we try our best not to leave any questions unanswered and to give you a feedback. For now, we also apologize for the delay. We have 9 minutes delay according to our original schedule. We will meet us at 12:15. If I am allowed, I will give you more 5 minutes to the break. So we will meet us 20 after. Wait, I have to check again. The original plan was to meet at 12:30, but we will meet at 12:35. Since we have 9 minutes late now, we will divide it 5 minutes for us, 5 minutes for you. So we will meet us at 12:35 here again. Thank you for participation again, for your attention, and see you soon again. Enjoy your break.
Razgar, don't you want to take a photo with Sarah?
Ah, yeah, it was not my original idea, so I forgot it, Sarah. I apologize for this.
Yeah, I also forgot, don't
Yeah,
worry.
sure. So
Okay.
everybody could just open a camera,
Cynthia,
please.
will you take when I say?
I see many cameras now. And Hania, you take over to take photos, right?
Yes.
Mm-mm.
The best chair of
But
ISWA.
do you have the first page, Cynthia?
Should I do anything from my side?
I'm waiting for Cynthia to.
I don't see she's here, but yeah.
Is it good? Okay, then 1, 2, 3. Okay, thank you.
Thank you,
Thanks.
guys, and enjoy your break, your lunch, your dinner, and see you after the break, 12:35.
I need to log off, so I say bye-bye to everyone and thank you very much for the invitation.
Thanks, Sarah, again.
Bye-bye. Thank you.
Good afternoon from my side. Good evening for some of you. We are now back to begin with the last presentation of Dr. Fabian Diaz. I think he's also based in Germany and not far away from me. I hope I'm not wrong. So Dr. Diaz, if you are here with us, would you please unmute yourself and share your screen to check the IT?
Hello everyone.
Hello, we can hear you.
Perfect. Nice to meet you. Thanks for the invitation, first of all. Yeah, I am not based in Germany. I am based very close to Germany. I actually based in Latvia, but which is a small country in the Baltics, very close to Germany, yes. But I am actually not from Latvia. I'm from Colombia. So
Okay.
yes.
So I apologize.
No.
apologize
It
for
is
this.
totally fine. It is totally fine. Do not worry at all.
Yeah.
Thanks again for the invitation and for having me here today. If you want to,
we
I
thank
can.
you for your time, for your presentation, and your input into our training course. If you are ready, you could probably start sharing your screen. If we can see. Yeah, we can see your screen now.
You can see it. Okay, perfect.
Yeah, so now I give you the floor and you have exactly 1 hour as planned before.
Perfect. Thank you so much. And thank you everyone for being here. It is my pleasure to try to share some of the knowledge and experience that I have in life cycle assessment. Just before starting, I would like to make a brief introduction on who I am and what I do. I am a chemical engineer. I have a master's degree in environmental science, and I am finishing my, I'm about to finish my PhD in environmental engineering with a strong focus, of course, in life cycle assessment and life cycle sustainability evaluation. I have around 7 years of experience in the field. I have been doing life cycle assessment, life cycle costing, mainly for energy sector at the beginning. Then I pivot towards LCA for the chemical industry. But in the last couple of years, I have been focused most of all in the construction sector, performing environmental product declarations. Yeah, so that's a little bit about my professional background. As I mentioned before, I'm from Colombia, but I live in Latvia. And I have been here for 7, 8 years now. So the idea today for me is to cover life cycle inventory. I will be talking about a little bit of technical aspects of life cycle inventory. I have prepared some also kind of a practical guide on what are the main tips and in collecting life cycle inventory and making good use out of it. Yeah. So let's start by saying that life cycle inventory or inventory analysis is the second step in the life cycle assessment methodology. The first one is defining goal and scope. Then you have the life cycle inventory. Then it comes the impact assessment, and finally the interpretation. When we talk about life cycle inventory, we are talking about basically 3 things: collecting activity data, collecting environmental profiles, and how to actually perform the collection process of the data, right? Now, in my opinion, life cycle inventory is the most important part of an LCA. Let me elaborate on that, because many will say the most important part is the goal and scope, and they are not wrong. What I mean here is that life cycle inventory can be very important, if not the most important, because of 2 main reasons. It's the step that requires most of the resources. It takes most of the time for the LCA practitioner supporting the company, for example, that is interested in doing the LCA. It takes most of resources because usually companies need to allocate people and resources and software into collecting the data, but also because depending on the quality of the data collected, you will impact your results. If the quality of your data is very low, you cannot expect too much of your results, right? Because the impact assessment method, for example, they already come in the softwares that we use for life cycle assessment. Yeah? And there is not much to change there. They are widely accepted, developed by scientists, so you don't really need to touch them too much. So what it will give the quality of your results is the data collection and the quality of that data, right? As I was mentioning, the results can only be as good as your data. This is gaining more and more importance since life cycle assessment and results are coming from life cycle assessment in form of product carbon footprint, in form of environmental product declarations, are gaining more relevance at the decision-making factor. It's a decision-making factor nowadays. Companies are not just now looking at cost of material, but also at the embodied carbon, if we're talking about buildings, or the product carbon footprint of materials. So it is important to have good results and accurate results, so you can actually show what is the real value of your product, right? So what are the typical life cycle inventory steps? So, well, I like to say that we can split it in 4 main steps. The first step, first of all, life cycle inventory is clearly defined in the ISO 14044. So if you have access to this standard, you can go and read more about it. From my experience, and especially if you, it is the first time that you are making an LCA, I like to think that these are the 4 main steps. The first one that I really recommend is always make a flow chart of your product system, defining the so-called system boundaries, defining what are all the unit processes or stages in the life cycle that you are going to put under the study. Yeah, that's the first thing. Then collect the data, put that data, when I talk about collect the data, is focus on resource use, emissions, materials, energy. We will talk in deep about the type of data that we need to collect later. Once you have collected the data, you need to actually put that data somewhere, usually an LCA tool. Or you can, if you are using, for example, Excel or other type of spreadsheet calculators, you will need to collect the so-called characterization factors. Characterization factors are what in product carbon footprint are called emission factors, but characterization factors are including other type of conversion units, like how much of water footprint represents using certain material, or how much land use represents certain process. Those are characterization factors in a nutshell, putting it very simple. Once you have collected the data, you need to build a model of your product system that is usually done in the same software while you are matching your activity data with those environmental profiles or characterization factors. And finally, you calculate resource use and emissions. Calculate resource use and emissions is not the same as actually making the impact assessment model. What I mean here is you might collect certain data, like, for example, wastewater production. I calculated that I'm doing an LCA model for a factory making whatever, and there is certain amount of wastewater produced every year. 10 cubic meters, 100 cubic meters, whatever. And there are certain, of course, there is certain quality of that wastewater. Yeah? It has a VOD, a COD, etc. There are suspended solids in that water, organic material. So collecting that data and then calculate resource and emissions is exactly transforming whatever process you identify into how much emissions it takes and how much resources it takes and how much and the quality of those emissions. That is the so-called life cycle inventory results. This is something that nowadays is made by the software itself. Once you put that lifecycle inventory, that data into the software will automatically calculate those lifecycle inventory results using the different characterization factors embedded also in the software. This is an iterative process. What it means is in many cases, after you have collected or you think that you have collected all the data, you need to go back. And you need to go back to your goal and scope to understand if all the data was actually collected, or maybe there is some data that you cannot have access to, and therefore you need to think if maybe you actually need to change the scope of your study. Right. So let's talk now about the data. What is this data that I'm talking about? And I keep talking about data collection, and this is a very common question. What it means collecting the data? What is the data I need to collect? What I mean is that lifecycle inventory, from my perspective, from a very practical view, is split into two things or two types of data. I need activity data and I need environmental profiles for that activity data. What is activity data? Activity data is how much of a material I am consuming, how much of electricity I am consuming, how much fuel I am using in my process. What are my direct emissions in terms of, for example, CO2 emissions or methane emissions or wastewater flow? That is activity data. But activity data itself will not be enough to make an LCA. You need an environmental profile for each one of those activity data points. What is an environmental profile? An environmental profile is a set of results in terms of impact categories. For example, an environmental profile of a material could be the carbon footprint. How many CO2 equivalents per ton of a material is produced? That will be an environmental profile, very focused only in global warming, in climate change, right? But since LCA tries to be a holistic methodology, you have a lot of other impact categories. Yeah, so an environmental profile should cover other impact categories such as abiotic depletion, freshwater use, eutrophication potential, and many more, depending on the impact assessment methods that you are using. So, what are sources of activity data? I will talk in detail about it, but usually, if we are talking from a company perspective, you have flow meters, you have utility bills, you have IT systems where all purchases and other exchanges are recorded. You have surveys. When we talk about the environmental profiles for that data, what are the typical sources? You have environmental product declarations, especially useful in the construction sector. You can look for LCA papers. Yeah, you can look in current scientific literature to see if there is a study on the material that you identified, and therefore you can have an environmental profile or LCA result for that. You have LCA databases like EcoInvent and many others. And you can also create customized processes. If you are an experienced LCA practitioner, if you have access to primary data in terms of how certain process is conducted, you can create your own process. Now, when it comes to activity data, we can classify activity data basically in 4 blocks. We have energy inputs, raw material inputs, ancillary inputs, and other physical inputs. Yeah, so all my inputs, I can have them there. I have another type of LCA activity data, which are my outputs in terms of emissions to air, emissions to water, emissions to the soil, things like that. Those are things that I need to focus. Whenever I'm doing an LCA, I should figure out if my foreground system, if there is primary data for my foreground system. Foreground system is that system that I have control on, like operational control or financial control. If I have operational control on something, it is very likely that I know, or I should know, how much water I am releasing to the environment, to the river, to a lake, or to the sewage, to the municipal water system, and what is the quality of that water discharge, and other type of emissions. The other type of activity data that I need, of course, is what is my product, what are my co-products, if they exist, and waste. Yeah, and there are other environmental aspects that could arise in life cycle inventory, like, for example, like some. We will see that in detail later, but for example, I need to also understand how, not only how much waste I am producing, but how that waste is being treated. I will also need to collect information about how my waste is being treated, and I will explain why that is important also in a few slides. How data collection looks like once you have gone through the process of collecting your activity data. Well, as I said before, it is highly recommended to create a flow chart, as you can see here on the right. And what you should do is create those flows for all those things that we saw before. Inputs of energy, raw materials, or other physical inputs. You have your emissions, and you have your studied product, other products, and waste generated. And this is what you want to do per unit process or per stage in your life cycle. And you will do this for every stage in the life cycle within the system boundaries that you are, of course, that you have defined previously in the goal and scope. So this is a very good view of what you should do in paper or in some kind of software to have a visual representation, because if you have a visual representation of your process, it is easier to spot if you are missing some data or not, right? Now, I mentioned unit of process or unit process. There are different types of unit processes, and as I said before, drawing those boxes is very useful because it allows you to identify those flows that you need to collect the data for. You can have very simple processes with the input of a couple of materials only and a single output, or you can have a bit more complex ones, like the ones here illustrated. In a multi-input process, a special attention needs to be placed on the type of materials entering the system. You can have semi-finished products that you are purchasing from an industrial actor. You can have raw materials or even elementary flows. You can, for example, you can be chopping wood for your main product, and that will be elementary flow. Yeah, so you need to identify which one are semi-finished product, which ones are intermediate material, which one for raw materials. You can have even waste coming into your process, because now when we are trying to move to a more circular world, it is very likely that, and it's already happening, that waste and secondary materials are being used to substitute, to replace some virgin material. So you need to exactly know what type of material is coming into your process, because depending on the type of material, they will have different environmental profiles. Even if the material is the same. Example, you are using woods or wood chips for producing energy. If you are using wood chips, purchasing that from an industrial actor, that is a product, right? You are purchasing a product and you are using it for energy extraction. But if you are using wood as wood barks or wood chips from a previous process where that flow was a waste, then the environmental profile of that material is different because it's a waste and not a product. I will go a little bit also in detail that later. In multi-output processes, on the contrary, the attention is focused mainly on how to distribute the environmental impact of your process among those outflows. Are they co-products or are they waste, and how should I treat them? The inventory collection is in this case not just about understanding how much of a waste is generated, but also, as I said before, what type of treatment that waste follows. Because depending on the LCA standard that you need to follow for your study, you might need to include the waste treatment activity within your system boundary. Some LCA standards allow you that you say, okay, I produce a waste, and if someone is gonna later use that material or that energy coming from the waste treatment, that someone downstream, the so-called subsequent system, should take care of the impact related to treating that waste. In other LCA standards or product category rules, such as the case of environmental product declarations, they do not allow you to do that. They say, if you produce a waste, you need to take care of the waste treatment. This is the so-called polluter pays principle. If you are the polluter, you are absorbing the environmental impact resulting from treating your waste. And that, of course, not only impact your model, but your life cycle inventory, because then you need to understand what is actually happening with that waste. In the case of co-products, that you have co-product A and co-product B, what you need to collect information is things like what is the revenue that is coming from these co-products. Because if you have really one product that is bringing most of the revenue, basically your factory, your unit process exists because you want to produce product A, then it makes sense that you allocate most of the environmental impact resulting to that product A rather than co-product B, right? And that basically depends, and what I mean here is that you will need to allocate those impacts either by physical relationship, the so-called mass allocation, or you will, in some cases, need to allocate that impact based on the economic factors. If you say, and when basically the idea behind economic allocation is, if I have two products and the revenue from each of them is are very close to each other, then even if my product A is, I like to think that is my main product, then maybe I need to, but if the economic revenue is almost the same or close, then maybe I need to use better an economic allocation, because my unit process also depends on the revenue from product B. In those cases, I will use the economic value of those products to allocate the environmental impact. So that is also part of the inventory collection, because as you can see, I will not only be collecting data about amount of material, but also about the economic value of those materials. Now, let's talk about LCA, a little bit about LCA for waste management. When dealing with one question, Gar, I see there are some questions. Should we deal with them at the end of the session, or should we take them now?
We usually have a discussion session after every presentation. So we have about 15 to 20 minutes after your presentation to answer the questions.
Okay, perfect. Thank you. So I will try to address them then at the end. Let's see a little bit of how to deal with waste treatment and life cycle inventory collection. A typical comparison when we deal with waste treatment is landfilling and other type of treatment. Yeah, these can include separated waste stream. This figure is at general level for solid or for wastewater. It will be for any of those. When we talk about waste, the first thing to understand is that we have different separation sources. And this is important that you understand different separation sources while collecting your inventory, because in the LCA databases, you will find processes reflecting those type of separations. You can have separation at the source, which is, for example, what we do at our house or in our buildings when we put plastic aside and carton aside and organic materials aside. That is separation at the source. Yeah? And therefore, that waste flow will not need heavy sorting activities in the waste treatment process. But you could all, and there are specific data sets that reflect those type of scenarios. But you could also have centralized separation, where the separation occurs after the whole waste flow is collected, which is what we still have in many countries, where you put everything in the same bin, or where you put plastics in the same bin, but plastic still needs to be sorted into the different type of plastic, because there are some plastic that can be more easily recycled than others, right? You also have data sets representing those type of processes in the commercial database for LCA. So it's not only, again, about collecting activity data, but understanding how those things take place to see what is the right inventory to collect. Yeah. Be aware that this chart is not itself explanatory to compare different options, since treatments produce different alternative material or products. And there is also the case of closed loop recycling. And there is the case that I will cover in the next slide about how to allocate these flows. And what I mean is, to whom does the resulting impact from waste treatment correspond? As I said before, this will depend on the standard that you are following. You will need to decide if the resulting impact from the treatment correspond to the waste producer, following the polluter pays principle, or if the impact of any of these treatment should be allocated to the user of the resulting flow, yeah, or maybe using a hybrid approach, and then how to split the impact resulting from the waste treatment scenario. Yeah, so let's look at how to, or how is usually this deal with. Usually what we need to do to understand what is the potential impact and also the potential benefit of having waste treatment that result into further products is by what is called in ISO 14044 a system expansion. Yeah, system expansion is what we do to understand how our co-products or resulting secondary materials benefit a further system. So in this case, for example, the inventory collection grows in complexity because, again, you are expanding the system, and now you also need to collect the data to understand how that flow will be used in the future and what type of material or energy is going to be replacing. This is the so-called, this that we have down here, this is the so-called avoided impact. You are treating a waste. When you treat the waste, you reach what is also called in life cycle assessment as you reach the end of waste state. So that flow is no longer a waste, and it becomes a secondary material or a secondary fuel. And it has a use in the market. Yeah. Since these flows have a use in the market now, they are theoretically, and in reality, it can be like that, they are avoiding the production of a product from the business as usual paths. For example, you are recycling plastic, and that plastic is actually placed in the market and being used by a company to make new bottles, then you are avoiding the production of new plastic from the petrochemical industry. As I mentioned before, how much of the impact of creating that treatment is to be allocated to one actor here or to the actor actually using the product. That depends on the specific product category rules in place, if you have any of those. Now that we have seen this issue of how to allocate the impacts in waste management, it is important to know that there are several allocation methods. We have the simple cutoff, where you decide, okay, I'm following the polluter pays principle and everything goes to the waste generator. Or no, I am saying that all the impact from the waste treatment should be allocated to the user of that of that recycled material, because that actor is actually the one taking advantage of the material. So that is simple cutoff. You have cutoff with economic allocation, where by economic allocation you say, okay, 20% corresponds to the waste producer and 80% to the user of the resulting flow. And you have many more type of allocations you can have. You can use the circular footprint formula from the environmental footprint method. You can have 50-50 methods, or you can have allocation at the point of substitution, which are, in my opinion, the most useful or used ones in research, at least. Another very simple way to see how to deal with waste in life cycle assessment and when collecting data is by looking at this very insightful figure that is, sorry, I forgot to put here the source. It's from EPD International, and it's product category rule for construction products. So as you can see here, we have a waste, a material that comes from a building. We transport that waste until the waste processing facility, and you process that waste until reaching the end of waste state. Yeah. After that, if there is no need for landfilling or for waste incineration, you will have a flow that can be reused or recycled, and therefore will substitute a primary material. You can have a flow, a material flow, that can be used for energy recovery, and therefore will substitute certain type of fuel, right? Or if you have waste incineration in your end of life as your waste treatment, then you will have energy, and that exported energy will again substitute some kind of heat or electricity. Yeah, so this is a figure for you to pay attention to. PCR's product category rules are for free. They are very good standards. They're very specific. You can download them from program operators of environmental product declarations. All you need to do is to go to the web page and look for those documents. They are publicly available. Now let's see a little bit more about life cycle inventory and wastewater management. As I said before, this is a typical system boundary. You have production of drinking water in this case. You use it, then you collect. So then you have the wastewater flow that usually is going to the sewage. You have some type of collection, which is the sewage system itself. You have production of chemicals to treat that water, and then you have some treated water. There's certain part of the sludge that will go to landfill, but also depending on the technology used for wastewater treatment, you could have production of energy, most likely through some kind of anaerobic digestion. Yeah, and here again we have the issue of how to allocate impact resulting from those type of flows. So this is just an example that what we saw before does not only apply to solid waste, but also to wastewater treatment scenarios. In practice, if we are talking about how to do this in an LCA software, what it means is that you're going to model either you have access to the primary data on how the wastewater process takes place in terms of material and energy consumption. resulting flows, composition, and how they are dealt with downstream. Or, on the other hand, you can rely on existing processes from those LCA databases that include many of these possible scenarios. This is especially true in the EcoInvent database. What I mean is, basically, if you don't have a lot of primary data on what is happening here, you can go to those to those databases and find scenarios for this already. You can even find scenarios, very detailed scenarios nowadays on wastewater treatment, different types of treatments. So that is just for your information. Finally, we have the closed loop recycling system, where waste flows are treated and the resulting flows are utilized within the same system boundaries. In this case, the most common option is not to allocate any credit or any impact other than those arising from the processes needed to treat the materials to the system. That is explained because those flows do not become exchanges to the technosphere or to the ecosphere, and consequently, there is no impact to the environment. And here you might wonder, but wait a second, then what is the incentive for a company to do that, right? To reuse materials and to create energy from those waste? Well, obviously, the company is most likely seeing a cost reduction from purchasing virgin material. And the company will also, by using this closed loop recycling, will also not see any increase in its environmental footprint, given that it's reducing materials and energy consumption already. So everything that I talked so far was very technical details on how to deal with waste treatment scenario. I want to go back to more practical aspects of the life cycle inventory now. As I said before, is the most intensive, time-intensive part of the LCA. Data availability varies depending on this system under study. You might need to adjust the study scope if data is lacking. That happens very often, unfortunately. You need to consider inputs and outputs as the one we saw already. Something very important that I haven't mentioned is when you draw those flow charts, sorry, you need to be very careful with mass and energy balances. This is something very important in order, especially if you are going to make, if your study is going to be third-party review, you need to keep consistency at the mass and energy level, and you need to check for those allocations. Mass allocation, economic allocation for products and co-products, and waste allocation for waste treatment scenario. Let's talk about data quality. I like to talk a lot about data quality because I focus a lot in that during my work. What I said before is
Fabian, usually when I give you the floor, feel free to manage the room rule also. Ask everybody to mute themselves.
Yeah, someone unmute themselves. So thank you. Yeah. So what I was saying is your results depend mostly on the quality of your inventory. And there are several factors that affect the quality of the collected activity data or environmental profiles. Those factors are usually temporal, and this is the so-called time representativeness of your inventory. What is time representativeness? Basically, it's a symbol of this. You have collected activity data for year 2023, for example. Yeah, you collected energy consumption for year 2023. But maybe the environmental profile for that electricity, if we are talking about electricity, the environmental profile was created using electricity mix from year 2021. Then there is not a matching between the activity data and the environmental profile. And the time representativeness of your data is poor in that case. There is also geographical representativeness. What it means is, if you are studying a process conducted in Colombia, my home country, but I am taking an environmental profile of the same process that is conducted in United States, for example, there is no geographical matching there, and then the geographical quality is reduced. The same happened with technology. There are many technologies to produce the same products. I need to make sure, or I need to try to do my best to ensure that the environmental profile for that technology is actually corresponds to the technology that is in the system under study. I have to pay attention to my sources. What are my sources? How trustworthy are them? I need to pay attention on how precise was the data collected. Were my numbers taken by someone based on estimates, or were those numbers calculated, or were those numbers actually measured? That makes a lot of difference. And and I also need to take an overall look to my system boundaries and check for the completeness, that all the data was actually collected, that I did not forget to check at one of those important flows that we saw previously. If we are talking about data sources, let's start by primary data sources. Primary data sources, for example, peer review studies that are compliant with certain type of standard. What are the underlying assumptions of those studies? I need to take a look at the LCA report or scientific article, and as I mentioned before, what was the process to collect the data? Was the data measured, or was estimated, or was calculated, or something like that? Ideally, you have measured data. If not, then the next level is calculated data, and the lowest level will be something like estimated data, because the uncertainty on the data grows. So primary data is that one, because we have primary data and secondary data. Primary data is that one that is collected directly from the activity in the foreground process. So it's coming directly from those activities under my operational control, or at least within the foreground processes, my system boundaries. Where do we usually can find this data? Usually we find primary data from flow meters, from utility bills, from environmental product declarations, if we talk about environmental profiles, from surveys, or from other stakeholders like suppliers or customers. Yeah, it's always better to ask your supplier if they have an environmental profile, or if they can give you more precise activity data than just assume how much, right? You can ask your customers how your product is being utilized. A clear example is if we are making an LCA on a washing machine, I will need to conduct most likely a survey to understand how much water and how much soap, for example, the users of that washing machine are putting into the washing machine, right? So that is primary data, data that you actually were able to collect. Then we have secondary data. Secondary data is coming from proxy points. And again, it could be activity data or environmental profiles. You can collect activity data from LCA databases. That is common for background processes. Like you don't know how much energy is required for a process, but you found in a certain database a process that is very similar to yours. Then you take, for example, the energy consumption from there. It's okay, but it's not primary data, it's secondary data. When it comes to LCA databases, we have free databases and also for purchase databases. Here are some of them, but there are many more. We have EcoInvent, which is probably the most famous one. You need to pay for it. You have Carbon Mine, you also have to pay for it. Some of these are for free, like Agro Footprint, I think, is for free. The MAT is for free. We have also social LCA databases, and many more. Now, how an inventory looks like in terms of activity data is very simple. Usually it's a table where you split your processes, your unit process, and you put the flows there. and the units of measure are also important. So this is a typical table of activity data for a unit process called anaerobic digestion in this case. Now we have 10 minutes to talk about LCA tools. Nowadays, when it comes to LCA tools, I think you can just honestly go to YouTube and look for demos or videos or tutorials on how those tools look like and how they are being used. So what I'm gonna focus here is mainly in my kind of subjective opinion on the pros and cons of certain tools that exist in the market now. First of all, we have the classic tools. Some of them are for free, some of them are not for free. When it comes to classic tools, which are mainly software packages that you need to install in your computer, we have CIMA Pro and we have Gabi, which I think is now called LCA for Experts or something like that, but everyone still calls it Gabi. They are very powerful tools. I like them very much, although it is true that they are not user-friendly at all. They require certain level of training, let's say, on how to use them properly. But in my opinion, they are still the most powerful because they allow you to play with impact assessment methods. They allow you to create new substances. They give you a lot of possibilities, right? We also have some LCA tools that are for free. We have the case of OpenLCA that in theory gives you the same capabilities as CIMA Pro or LCA for Experts, Gabi. Is widely used. A lot of companies and people in the research business is using OpenLCA. You save a couple of thousands of dollars per year, or you need to pay for the database. But the software itself works very well. We also have Umberto for free, which to my understanding, I have never used it, but to my understanding, is also very powerful. And we have Grid, which is a North American software and database. Now, in the last year, we have seen the coming of new tools. These are only some examples. There are many more out there. These are the ones that I have seen in the last couple of years, and they are gaining a lot of, let's say, they're gaining market and they are gaining visibility. There is one that is called MakerSide that they claim to be artificial intelligence power, and they have very good visualization of results. They allow you to create. Somehow, remember when I was talking about creating this flow chart for your process, they allow you to do that. They allow you to create your LCA model in this nice flow chart. So it is very user-friendly. We also have Erster, which according to them is very good for scaling up LCA. So if you have System Boundary, which is a company, a multi-output process that has 100 or 1,000 different products, Erster says that they are very good for that. And what I can say, they have used this software is that their user interface is very different to what we have seen. I have, I think, an image for in the next slide about it. It takes some time to get used to it, but it's very interesting, and it is indeed also user-friendly. And we have some other LCA tools under development, such as Carbon Graph, which relies a lot also in user-friendliness and graphical modeling of LCA. We have Root, we have Sapology, we have Sustainly. They are on their, I don't want to say beta because I think they're already in the market, but they are still, in my opinion, being developed, and they are promising. Most of these tools, they focus on user-friendliness, which is, of course, an issue. If we talk about the classic LCA tools, they are not user-friendly at all, but they are still and this is only in my opinion, classic LCA tools are still more powerful in terms of what an experienced LCA practitioner needs, right? But these new tools, they have a lot of potential because they're faster, being cloud-based. They are not, you don't need to install any software in your laptop. They are cloud-based, and they run also models faster than the classic tool.
We have Fabian. We have the last 5 minutes. If
Yeah,
you
I know.
if you take a couple more minutes, that would be fine.
Yeah. So as I mentioned before, we have emerging LCA software created for different purposes. This is an image, for example, of a software developed by the MIT called Sesame that focus on energy and in the energy sector. We have also the one that I mentioned before that is called Grid, mainly used for chemicals. It's a very good source of emission factors, cradle-to-gate emission factors, carbon emission factors. So, and it used to be only a database, but they also now have a software that you can install for free, and it's okay. We also, in the European context, we have now also many more options, cloud-based. There are some specialized in the chemical sector, like Alloc now. We have also this one, which I think I was mentioning before, MakerSite. Yeah, this is MakerSite. So as you can see, you can see results in a very graphical way. We have also Earthster that I mentioned before. It's like a planet, and you have your processes around your planet. Very interesting. Yeah. And finally, I wanted to show you an example of how CIMAPRO looks like. So CIMAPRO is, you don't have a graphical representation of the LCA. You have all the things in a list, and you need to create processes and assemblies, and you kind of drag the things into that list. Once you have done that, you select your impact assessment model that takes all the inventory that you put into your model and gives you results. And this is a typical visualization of results in CIMAPRO that is kind of a Sankey diagram or network, as they call it. And my last message for all of you is that LCA is very dynamic and wide field. It's very hard for a single LCA practitioner to know it all. There are different impact assessment methods, different standards, different product categories. And on top of that, every sector has its own characteristics. So it's not the same to do an LCA for construction product than for an energy system or for a waste treatment scenario as you saw. So thank you very much for the invitation, for the opportunity to be here, and for your attention.
Thank you very much, Fabian, for the very compacted with many data on the software, feeding data, and also covering the construction, which was new for our master course. We focus mainly on products in the morning and later get insight into waste and now into construction sector, wastewater treatment, well, different sectors of engineering. We can use lifecycle inventory. As usual, we have a list of questions. I will go through the questions first to get your comment on them. Open the list. The first question is from Leta. What are the other environmental aspects include? I think it was on one of your slides. I don't know which one was it. So if you can also feel free to go to the slides and give comment or just directly answer the question.
Slide number 7.
Number 7. Okay, thanks.
Okay, yeah, I think I covered that. Let me see, how can I navigate faster to the slides here? Yeah, other environmental aspects. Other environmental aspects are, as I mentioned before, is, for example, waste treatment scenarios. Other environmental aspects could be also the type of input material that you are having. And I touched this only slightly, but it is not the same to have a product than a co-product or a secondary material of your waste. And those are environmental aspects because those materials come with a different environmental impact. Yeah, so that's basically what I meant there. It's not only enough to look at the numbers and if it is a co-product or a waste, but you also need to understand what is the environmental impact associated to those flows and why.
A question from Vishaka. Is there any resource that could provide step-by-step guideline into using the life cycle inventory? And he mentioned also, or he mentioned a specific context for a wooden structure, for example, in somewhere in Himalayan context. Are
Yes,
there
there is.
any resource to?
Yes, there is a book, very complete book, and it's for free. And honestly, is one of the best, and it's for free. That is called the ILCD Handbook for LCA. It's a European document. You can Google it, and I'm sure you can download it for free. ILCD.
ILCD.
Yeah.
What is the complete title? That's ILCD Handbook, right?
Handbook, yeah.
Okay, I found it.
Yeah,
I share the link in the group in the chat box, so everybody.
It's very useful. It's a very long document. It's like 300 pages, if I remember correctly. But it's because it's super detailed, and it has, of course, a chapter for life cycle inventory.
It's exactly more than what you mentioned. It's 417 pages.
Okay.
But maybe the content is about 300 pages.
Yeah, I don't remember by heart, but it's very long.
Yeah.
But it's very good. It's very technical, but it's a very good source of LCA information.
So everybody,
speak.
You have the link now in the chat box. Just click and you will get the PDF. We will follow the questions from Solomon. In producing more than one product, what methods to be used to understand the share of the environmental burdens of the activity should be allocated to the product in question? Did you get the question, or I have to read it again?
I think we are talking about how to allocate, right? Impact between products. Yeah. As I mentioned before, there are two main types of allocation for co-products. One is the mass allocation, and the other one is the economic allocation. In the mass allocation, what you do is basically, let me see if I can write something here. Yeah, okay, I'm not going to be good at this, but for example, if this is 60% of your total output, and this is 40% of your total output, yeah? And basically what you will do is once you conduct the LCA for your unit process, you will allocate 60% of the environmental impact to product A and 40% to product B. So this is the simple mass allocation. There is also economic allocation, and an economic allocation, what you understand during the life cycle inventory actually is where you understand that is what is the revenue that each one of them brings. And basically, let me see if I can, yeah, because, okay, or maybe, let's imagine that we have the following scenario. You have 90% of the mass in product A, and product B is only 10% of your output in volume or mass, right? But when you look at your inventory, what you realize is that co-product B is actually, even when it is only 10% of the sales, because it's only 10% of the volume produced, during the life cycle inventory, maybe you realize that 50% of the income, economic income, is coming from product B. In that case, for example, and this is where there are rules on how to do this, but then the idea behind is that in this case, if you have a case like this, it will be erroneous to assume that only 10% of the environmental impact should be allocated to co-product B. Because in reality, the reason and the function, and this is why LCA is based on function and functionality, the function of your unit process is not really to only produce co-product A, is to produce both. And therefore, following, you will need to split in a more fair way the environmental impact between your co-products. And in this case, you will need to use the economic allocation for that. So in an economic allocation, you will distribute 50% of the impact to B and the other 50% to product A, even when the production volumes are so different.
So since we had a couple minutes delay at the beginning of the presentation, we take 5 minutes more to answer 2 or 3 questions, depending on the detail Fabian will provide. The question is, how do you address data quality and uncertainty in life cycle inventory studies, especially when dealing with complex systems and limited data availability?
Yeah, data quality, there is one basic way to tackle data quality. I mean, data quality, it is what it is. You can do your best effort in collect all the primary information you can, but there is always shortage of data, or there is always data that needs to be estimated or taken from a proxy value. And there is nothing you can do. You still need to do your LCA. And it will not mean that your LCA is wrong. What is important in life cycle assessment is to be transparent. And therefore, in LCA, there is something called data quality assessment or data quality rating. And there are specific methodologies where you assign kind of a score to the data. So if my activity data was measured and not estimated, then I give a very high score. If the time representativeness, geographical representativeness, technological representativeness is good, I also give a score. And then at the end of my LCA, for each item in my inventory, I have a score. And then I compute the whole score, and I have a data quality score, data quality rating, or assessment, depends how is it called. So that is the way on how to deal with data quality. Depending on that score, you can say how certain or uncertain your results are, right? Or you could also do, if we are talking about uncertainty, we could also do a Monte Carlo analysis. This is something that some LCA tools allow, when you can actually tell the statistical distribution of your inventory. You can run a Monte Carlo analysis and then tell what is the uncertainty in your whole LCA model. So those are the typical ways how to deal with it.
So we picked up 2 more questions. Before we go to the question of Dr. Fahim Uden, there is a question on, it's a unique questions on artificial intelligence. 2-part question. Yeah. Have you used MakerSite artificial intelligence power tool? When they say artificial intelligence powered, what is AI powered, the sensitivity or practitioners based on random forests? Do you get the question?
Yeah, maybe I didn't get the last part, but I think I can provide a general answer.
Okay.
I haven't used MakerSite personally. I have seen the demos. I have seen how it works. To my understanding, artificial intelligence is powering what artificial intelligence is doing, not only in this one, but in other tools that I have seen, is automatically dragging from the database the environmental profile or process or data set that correspond to certain activity data. So what I understand is this LCA tools relying on artificial intelligence is that once you input, for example, electricity in India, it will automatically drag from the database the correct or the closest representative environmental profile or data set for electricity in India. Yeah. So to my understanding, that's not only how this one, but other tools are working when using artificial intelligence. But there are other ways to use artificial intelligence, apparently now in LCA. There is also the possibility to read papers or environmental product declaration and extract the information from it. And it is also apparently now in some cases used internally by the companies, by manufacturers, to collect the activity data. Yeah, but
So we concluding with the last comment or question from Dr. Fahim Udin, and she is or he is asking. I apologize for the gender; it's a bit difficult to recognize. The question is: it seems that each software has its own domain. Can we integrate them to have a macro scale analysis?
I'm not fully sure I understand the question.
This is a little bit far away from my background, so me neither. I don't get the question exactly, but I repeat it in case it was the reading. It seems that each software has its own domain. Can we integrate them to have a macro scale analysis? If it's unclear, Dr. Fahim, can you unmute yourself and ask the question in case you are still with us? If not, we are going to end the session. Okay, so there is, if one software is good for emissions, but another is for products.
Yeah, no, in reality, I don't think there is such, I don't think software has fallen into those categories. However, there are softwares or tools that are specializing in different sectors. And here I'm going to be very subjective, but for example, I work in a company that we specialize in the construction sector, yeah? And we have an LCA tool for the construction sector only, more specifically for the concrete and cement sectors, right? At the same time, there are other companies that are developing LCA tools. I have seen, for example, something very specific for apparel, for clothing. There is also some tools that are very specific for certain chemical industries. So I think tools are going more in that direction than in emissions or waste treatment or products. So that's, in my experience, what I have seen.
So she got the answer. She thanked you also. We are ending the session. Thanks, Fabian, for the slides, for the presentations and the discussion session. If you have some questions left, we will share with you, and we would be kindly asking to provide us with answers so you could share with our participants.
Yeah, I will try my best. Yeah, we can do that.
Thank you very much and enjoy your afternoon.
Thank you.
So now we are coming to close the first day of our training course on life cycle assessment. For this, I will give the microphone to the chair of ISWA, Dr. Jalalipur, to give an insight about the Monday program. We have the second day and also closing the day of the training course. Hania, can you hear us, and are you still here? I can see you. So I give you the floor. For now, I would just say bye to everybody and see you on Monday with a new moderator. Have a nice evening, afternoon, and goodbye from my side.
Thank you, Razgar. Thank you, everyone, for staying with us till this moment. I should thanks all the members of the online discussion working group, especially Shiza Aslam. She has put a lot of time in planning and organizing and inviting and communicating, as well as Dr. Ashpreet Kaur, who is based in America. So for Monday, we have also a half a day plan. I think you all received, and there will be a little bit of changes because Sarah presented today. But we stick to the plan, and we will have the half day until 12, between 12 and 1. The session will be ended, and we have several presentation, including Shiza. So I hope that we can see a lot of you there. Further, I wanted to share my LinkedIn and also my email address, so that if you have any question regarding joining to the ISPA or also networking, feel free to reach out, and I would be glad to assist you in any ways regarding the young professional group. So about the assignment, yeah, I see in the chat, we will provide you later with the, also you will receive per email after the second day, email with the assignment. As previously, also from last year, the rule for the online trainings are that we will, those who are attending 90% of the training courses and also answer the assignment will receive certification from ISPA Young Professional. And yes, Sarah, yes, Shiza, unfortunately, we didn't have the chance to have the photos with Fabian, and I think if he's still there.
Fabian is still with us. Yep.
Yeah, Fabian, if you are still there, we would be happy to, if you can open your camera and we can have like, if you stop sharing, yeah, please stop sharing, and then we can have a photo all together.
I should apologize. This was my bad. For second time, I forgot to ask for
No worries. It was a long day. Yeah.
Yes, I am still here. I just don't know if I stopped sharing already.
Not yet.
Not yet. Okay, let me see.
I think you're still sharing your screen. I think it's a lovely background. I'm not sure from where that is.
This is weird. I don't
Honey,
know.
can you host?
Here it is. Yeah, I found it.
Okay.
Sorry.
Oh, perfect.
Sorry about that.
So, please, everyone, open your cameras. I know it's the last. Okay, we are having more and more in the first page. Yes, thank you. 2 more people. Yes, another one. Liz, if I can ask you to open your camera because you are in the first page. And okay, Cynthia, are you ready?
Yeah, I have already.
Okay, then
But let me see. For me, it's
the first page.
Yeah.
The first. Yeah, quick. 1, 2, 3.
Yeah.
Thank you very much. Have a nice evening, and I hope we can see you again on Monday.
Mhm.
See you. Bye.
Thank you very
Okay.
much.
All right, thank
Shida,
you.
nice to see you.
Thank you everyone for joining. Yeah. Yeah. Worth the effort. So thank you so much. Yeah, glad to see. See you all on Monday then.
See you.
Bye-bye.
Guys, where is the assignment? Does anybody know where the assignment is?
You will
We
receive
will
it per
be,
email.
yeah. You will receive
Okay,
an
thank
email.
you. Bye.
Hi, please can you share the time for South Africa for Monday?
I think South Africa, are you having the same time still as Europe, or you change your time?
I'm not sure.
Yeah, maybe you can do the online conversion because there are too many time zones, but the time session is set on Central European time. It should be same with South Africa if there is no daylight change, clock adjustment. Otherwise, it would be maybe 1 hour late for you. I think it would be 9:30 Central European and 10:30 for you. Please do check the online conversion if that's a problem.
Okay, thank you.
And we will get the slides.
Yes, all the slides will be sent, and also later on we will also provide the recording, and we will upload it also to the online discussion working group on the ISWA Young Professional webpage. You can also see other slides and recording of last year training courses there.
Thank you very much.
Yeah, no worries. So I'm going to close this session. Cynthia, did you download the chats?
No, sorry.
Okay.
Wait for me.
Yeah. Okay.
Wait 1 minute. Just to be careful.